Hello there, and welcome to the Sleepless Scientist, a quiet place in the cosmos where your thoughts can unwind and knowledge becomes a soft lullaby for the night. Tonight's journey will take us into the strange, luminous borderland between physics and life itself, a world where the smallest particles seem to whisper the language of living things. Together we'll drift through the mysterious realm of quantum biology, where robins find their way across oceans by reading invisible fields, where plants turn sunlight into life with impossible precision, and where even the air you breathe and the scents you know may be guided by the quiet dance of chance beneath all matter. But before you settle in and get cozy, I'd love if you could take a moment to like this video and subscribe, only if you truly find these quiet explorations enjoyable. And when you're ready, leave a comment to let me know where in the world you're listening from and what time it is for you right now. It's always such a joy to see all the places we gather from, each in our own little slice of time. Now, feel free to dim the lights, maybe turn on a fan for a soft background hum, and let's gently begin our journey into the strange and beautiful world where physics and life meet in silence. Where, just before dawn, the mist still clings to the grass, the air is cool and patient, and somewhere in the distance a bird stirs, one that carries the secrets of navigation written softly in its eyes. And if your mind begins to wander, that's perfectly fine. Let it drift. We'll still be here, quietly unfolding the story. I used to think of quantum physics as a thing that belonged only to the lab, to polished metal instruments, cooled atoms, and the controlled hush of vacuum chambers. There, particles behaved in ways that seemed almost supernatural. They could be in many places at once, pass through walls, or communicate instantly across space. Yet everything about those experiments felt distant from the messy, warm pulse of life. How could something so delicate, so easily disturbed, survive inside a living cell, where molecules crash and collide 1 billion times a second? The thought once felt impossible, until evidence began to suggest otherwise. The forest around me seemed still, but within every blade of grass and wingbeat of air, quantum physics is quietly at work. Deep inside the cells of animals and plants, particles are gliding through barriers as if they were made of mist. In the chlorophyll of leaves, waves of light move in perfect coordination, exploring many paths at once, choosing the most efficient route to sustain life. In our own bodies, molecules hum at specific frequencies, creating the scents and sensations that connect us to memory. It's as if the universe has hidden its most extraordinary tricks inside the most ordinary acts of living. For most of history, the line between physics and biology seemed solid. One studied lifeless matter, the other living things. But nature doesn't recognize such boundaries. Somewhere within this quiet forest, those lines begin to blur. Here, in the light that touches a leaf, or in the eye of a bird tracing invisible roads in the sky, we can sense something more. A delicate handshake between the quantum world and the living one. To understand what makes this world so strange, we have to travel smaller than sight, smaller even than imagination. Down there, particles no longer behave like little billiard balls. They become waves of probability, shimmering clouds of possibility. An electron, for instance, is not in one place until it is observed. It exists in all possible places at once, a spread of potential waiting to be realized. This is called superposition, though we might think of it more softly, as if the universe itself were undecided for a moment, holding its breath before choosing an outcome. And sometimes two particles can become mysteriously linked, no matter how far apart they drift. Change one, and the other changes instantly. This is entanglement, or as Einstein once called it, spooky action at a distance. You can imagine it as two coins tossed in opposite directions that always land showing the same face, even if they're on different sides of the planet. For years, such ideas felt too delicate to exist outside controlled experiments. In the cold vacuum of a lab, physicists can coax atoms into these fragile states. But inside the warm chaos of biology, surely the coherence would crumble instantly. Yet nature seems to have found a way. Somewhere between chaos and order, life may have evolved to use the weirdness of quantum mechanics, not by accident, but by design. As the first rays of sunlight rise over the forest, I watch a small bird lift from a branch. She tilts her head as if sensing something beyond the horizon, something not seen but felt. Every year, thousands of robins travel thousands of miles with uncanny accuracy, guided not by landmarks or stars, but by Earth's invisible magnetic field. The puzzle is ancient. How could a creature so small detect a force so faint? Even a compass needle barely stirs without frictionless bearings, yet a robin's heart and wings respond effortlessly. The answer, as we now suspect, lies deep within her eyes, and deeper still in the strange quantum connection between particles of light and molecules of life. There's something beautiful in that thought. The same physics that governs collapsing stars and distant galaxies may also help a bird find its way home. The same wave equations that describe electrons may also shape the smell of mint, or the turning of a leaf toward the sun. It's a reminder that the universe is not divided between the living and the inanimate. It's one continuous fabric, woven of the same threads, vibrating at scales both cosmic and cellular. Standing beneath the branches, it's easy to feel small, but not insignificant. The ground hums faintly, not with sound, but with energy. The gentle dance of atoms, of quantum waves meeting, splitting, and recombining in endless patterns. Somewhere in that hum lies the story of how life began, how it endures, and perhaps even how it thinks. The forest, in its quiet way, is a living laboratory. Every leaf a solar panel tuned to quantum rhythms, every nerve and feather a messenger of invisible forces. As I listen to the morning settle, I realize that what we call weird in physics may simply be what life has always understood. The same rules that make particles behave unpredictably also allow living systems to adapt, to sense, to transform. Perhaps evolution itself has been conducting experiments for billions of years, finding ways to make quantum effects stable, useful, and beautiful. The robin circles once above the trees, then disappears into the light. In that moment, I feel the thread connecting us, her wings, the sunlight, the particles in my breath, all part of one quiet equation, written in the same invisible ink. The forest is no longer a place of separate things, but a single unfolding field of possibilities, guided by rules that are strange, subtle, and astonishingly precise. And if we follow that thread a little further, it will lead us to one of the most remarkable discoveries of all: how a bird's humble sense of direction may be the first clear sign that life itself is fluent in the language of quantum mechanics. The idea that a bird could use quantum mechanics to navigate sounds like something out of a dream, a poetic exaggeration whispered between stars. Yet as strange as it seems, the evidence is mounting. Imagine a creature weighing barely a few ounces, able to cross continents with precision so uncanny that even our best instruments struggle to match it. Every winter, the European robin lifts into the cold sky and travels from northern Europe to the warm valleys of Spain, tracing a path thousands of miles long. No road signs, no landmarks, only the silent geometry of Earth's magnetic field. For decades, scientists believed that birds must carry some kind of iron-based compass in their beaks or brains, perhaps small crystals that align like needles. But experiments began to tell a different story. When robins were kept in a magnetic cage, one that allowed scientists to rotate and tilt the magnetic field at will, the bird's internal sense of direction changed accordingly. They adjusted their orientation, always following the field's invisible lines. And yet, if the experimenters dimmed the light, the compass failed. It returned only when the room glowed with soft blue light. The clue was hidden in the colour of the morning sky. Inside the robin's eyes lies a delicate molecule called cryptochrome. It acts a bit like a camera sensor, but one with a strange quantum twist. When a photon of blue light enters the eye, it strikes this molecule and frees an electron. That electron doesn't travel alone. It leaves behind a twin, and the two become entangled. You can picture them as partners in an invisible dance, spinning in perfect coordination no matter how far they move apart. The robin carries millions of such pairs, forming and dissolving in rhythm with every flutter of her wings. Now here's where the magic begins. The direction of Earth's magnetic field subtly changes the pattern of that entanglement. You might imagine it like two dancers moving on a floor that gently tilts depending on which way they face. A slight shift in angle changes the way their steps fall together. In the robin's eyes, that tiny shift alters the outcome of chemical reactions inside the cryptochrome molecules. Different reactions send slightly different signals to the bird's brain, creating a visual map of magnetic directions, perhaps a faint pattern of light and shadow over the normal image of the world. It's breathtaking to think that navigation, a behaviour we associate with maps and compasses, may depend on quantum entanglement, a phenomenon so delicate that physicists must isolate it from all noise and heat. Yet this small bird maintains it effortlessly, mid-flight, in the turbulent warmth of living tissue. It's as if life itself has learned how to cradle quantum fragility in the palm of chaos. Even Einstein, when faced with this strange connection, refused to believe it. He called it spooky action at a distance, because it seemed to break every rule of common sense. How could one particle affect another instantly, even when separated by space? But experiments have confirmed it again and again. These partners are truly linked. They share a single state, like two reflections of one image. Change one, and the other follows, as if space between them didn't exist. In the robin's eyes, this entanglement doesn't last forever. It flickers for a few millionths of a second, just long enough to matter. The bird's biology renews these pairs continuously, maintaining a gentle pulse of quantum whispers within its vision. Some researchers describe it as a compass made of light, tuned to the faintest tremor of Earth's field. Others simply call it beautiful. There's a quiet irony here. In laboratories across the world, scientists spend years trying to isolate and control entanglement, cooling atoms to temperatures colder than outer space, surrounding them with magnetic shields and silence. Yet in the natural world, a robin manages the same feat with nothing more than sunlight and soft feathers. She doesn't know she's performing quantum computation. She simply follows the tug of instinct written in her cells. You might wonder how such a mechanism could ever have evolved. Nature doesn't design with intention. It experiments endlessly, generation after generation. Over time, the systems that survive are those that work, whether or not their creators understand why. If a few random mutations happen to align the chemistry of the robin's eyes just right, allowing entangled electrons to persist long enough to influence direction, then the bird that could follow magnetic lines more accurately would find its way home more often. Gradually, what began as a fragile accident became a survival strategy encoded into life itself. It's humbling to imagine evolution as a kind of quiet physicist, testing ideas over billions of years with the patience of the universe. What took human scientists a century of equations to glimpse, nature discovered by simply being alive. When we watch a bird migrate, we often picture instinct as something ancient and mysterious, born from repetition. But now we see it in a new light. Instinct might be not only biological, but quantum, a silent collaboration between matter and the forces of the planet. The robin doesn't read the magnetic field as a number or formula. She feels it as a pattern of reactions, a shimmer in her sight. She doesn't think in terms of electrons or spins, but her body is fluent in that language. At dusk, when the sky begins to cool, the bird lifts again. Her eyes catch the fading blue light, just the wavelength that awakens her compass. Somewhere beneath that glow, entangled electrons begin their dance. One turns, the other follows. A whisper passes between them faster than any signal we can send. She tilts her wings and sets off toward a horizon she's never seen, guided by a physics older than her species, older even than the Earth's iron core. If you stand beneath her flight path and listen closely, there's no sound of technology, no hum of engines, only the hush of air passing over feathers. Yet within that silence is one of the most profound communications in nature, a dialogue between a living being and the fabric of space itself. The robin vanishes into the twilight, but she leaves behind a thought that lingers. Maybe the strangest part of quantum physics is not that it happens in laboratories or inside equations, but that it happens within life, quietly, persistently, without needing our permission to exist. And as we follow this thread further, we find that the robin is not alone. The same invisible rules that help her find her way through darkness may also shape the scents that guide a bee to its flower, or the smell that wakes a memory in your mind. The path now carries us toward another sense, one that also listens to quantum vibrations, though this time not with eyes, but with the quiet instrument of the nose. Night settles over the northern woods. The stars have come out, steady and cold, and a robin perches on a branch so thin it bends under her weight. She tilts her head, as if listening to something beyond the reach of sound. The air smells faintly of frost and pine. In a few days, she'll begin her journey south, across clouds and rivers, guided by something no human has ever seen. Centuries people have wondered how such small creatures find their way across vast distances with such certainty. The sky offers few clues, and the Earth's magnetic field is too faint for any known nerve to feel. Yet the robin seems to sense its pull effortlessly, as though her eyes could read an invisible map painted on the air. Biologists have tested her mystery again and again. They placed robins in circular cages, each lined with soft paper cones. When the lights dimmed and the season turned, the birds scratched the cones in a single direction, always toward their migratory path, even when clouds hid the stars. But when scientists surrounded the cages with artificial magnetic fields and rotated them, the robins changed course. They turned not toward the sun or memory, but in perfect alignment with the direction of the field. Somehow they could feel what no instrument could measure without help. The real surprise came when one researcher decided to darken the room. When light vanished, the robins lost their sense of direction entirely. It returned only when a soft blue glow filled the space. Red light, yellow light, nothing worked. Only blue. The clue lay hidden in that colour, the same hue that tinges the early dawn when migration begins. Inside the robin's eyes is a pigment called cryptochrome. It's a light-sensitive molecule shaped to capture photons, tiny packets of light that travel from the sun through the sky and into her vision. When one of those photons touches cryptochrome, it doesn't simply disappear. Its energy frees a single electron inside the molecule, sending it spinning away while another stays behind. For an instant, these two electrons exist in a strange relationship that defies distance. They are entangled, bound by an invisible thread so delicate that even the flutter of atoms might break it. In that quantum connection, each electron holds two possibilities at once, like a coin that is both heads and tails until it lands. The pair might be aligned in the same direction or opposite, red-red or red-green, depending on how they spin. What matters is that they share their state completely. When one flips, the other flips too, no matter how far apart they drift within the molecule. Einstein once called this kind of link spooky action at a distance, because nothing, not even light, should connect two particles faster than light itself. But experiments proved again and again that entanglement is real. The robin, it seems, carries within her eyes one of the strangest truths in physics, As the bird turns her head beneath the stars, the angle of Earth's magnetic field changes. That change affects the entangled electrons, tilting the balance between their possible states. In one orientation, the pair might favour one chemical reaction. In another, they might favour its twin. Those reactions, in turn, send different patterns of signals through the robin's nervous system. To her, the invisible field becomes visible, not as colour or shape, but perhaps as a faint shading over the world, a pattern of brightness or darkness showing which way is home. It is a compass not made of metal, but of chemistry, not built, but grown. And it works only when the sky is blue, when photons carry just the right amount of energy to awaken the entanglement. If the light shifts toward red, the delicate connection fails and the compass falls silent. Imagine the elegance of it. A field so weak it can barely nudge a compass needle can still whisper to a robin's brain through a quantum signal lasting less than a millionth of a second. The fragile state between those two electrons must survive long enough for the chemical reaction to finish, and yet it does, even within the warmth of a living eye, surrounded by moving molecules and constant noise. In laboratories, physicists must cool atoms to nearly absolute zero to preserve such coherence, but the robin does it while flying through a storm. No one knows exactly how she protects it. Perhaps the surrounding molecules form a natural shield, a cradle that quiets random vibrations. Perhaps the rhythm of her biology, her heartbeat, her breathing, the steady cycles of day and night, continually resets the connection, allowing it to be born and reborn with every flash of light. Or perhaps nature, over millions of years, simply stumbled upon the chemistry that made it possible and never let go. Whatever the reason, the effect is the same. A bird navigating by quantum entanglement, carried through the sky by physics once thought too fragile for the real world. There's a quiet beauty in the thought that life can hold such complexity so easily. The robin knows nothing of electrons or spin. She doesn't calculate magnetic angles or understand that she's part of an experiment written in the language of subatomic particles. She simply flies. Her migration is not the triumph of knowledge, but of harmony, her body tuned to the planet's faint magnetic hum. When I think of her crossing continents, wings flashing against the wind, I imagine the invisible pattern she follows. The sky is her map, the field her road. Each beat of her wings renews the entanglement in her eyes, each pulse of blue light recalibrating the compass that no one can see. The physics that Einstein found unsettling becomes, in her, a quiet certainty. If you stand on the ground beneath her path and look up, you might see nothing but a dot against the distance. Yet in that dot lies a secret older than flight itself, the ability of life to borrow from the strange order of the quantum world. The robin's journey is both mechanical and mystical, a body of feathers and muscle guided by a whisper between two particles of light. It makes you wonder what else life has learned to hear. If the robin can see magnetic whispers through entanglement, perhaps other creatures have found ways to sense the unseen, to turn quantum subtleties into survival. Maybe deep within us too there are echoes of that same fluency, small ancient mechanisms that translate the invisible into feeling, thought, and motion. As dawn returns, the robin lifts from her branch and begins her long journey south. The stars fade, but her compass does not. The soft blue of morning is enough to keep her direction clear. She flies, guided by a phenomenon that even physicists still struggle to describe. Her heart steady, her path precise. And as the light grows stronger, we might ask ourselves, if sight can hear such magnetic whispers, perhaps another sense, one closer to emotion and memory, can listen to something else entirely. Maybe our noses too are tuned to quantum music. When physicists speak about quantum entanglement, they often do so in whispers, not because it's mystical, but because it's fragile. In the laboratories where this phenomenon is studied, the conditions are so delicate that even a stray vibration from a passing truck or the faint warmth of human breath can destroy the effect. To keep entangled particles linked, researchers must cool them to near absolute zero, isolate them from every sound, and suspend them in near perfect emptiness. Only then, for the briefest moment, can they remain connected. 2 points of the same invisible thread stretched across space, and yet, in the warmth of a living robin, inside cells filled with water, chemicals, and constant motion, this same fragile connection somehow thrives. The entangled electrons in her eyes are born from sunlight, live for just a fraction of a heartbeat, and vanish, only for new pairs to appear a moment later. It's a process so subtle that no instrument could ever track it in real time. But the bird doesn't need to measure it. Her biology already knows the rhythm, the timing, the balance between chaos and order. How can this be? How can entanglement, that most delicate of quantum phenomena, endure in such a noisy world? Perhaps the answer lies not in resisting chaos, but in learning to use it. In the robin's eye, the molecules that cradle those entangled electrons are not rigid. They flex and sway with the pulse of life. The vibrations of nearby atoms, the gentle noise that would destroy coherence in a laboratory, may actually protect it here. By vibrating in just the right way, they keep the entangled pair from drifting out of tune. It's as if the chaos itself becomes the rhythm that maintains the harmony. Imagine a candle flickering in a storm. A physicist would try to shield it, to build walls and close the windows, but nature does something else. It teaches the flame to move with the wind, to bend rather than break. The robin's entanglement may work the same way, not by isolating itself from disorder, but by dancing within it. Inside the cryptochrome molecule, this dance takes the form of continuous renewal. Each photon of blue light that enters the robin's eye resets the system, creating a fresh entangled pair just as the previous one fades. Millions of these pairs appear and vanish every second. The bird's compass doesn't rely on one perfect state, but on a steady flow of imperfect ones, overlapping like ripples on a pond. The overall pattern remains stable even as the individual connections flicker out. It's a strategy that nature uses often. Resilience through motion. You can find the same idea in the beating of a heart or the fluttering of wings. No single beat or stroke defines the pattern. It's the repetition that creates endurance. Entanglement in this sense becomes not a frozen link between particles, but a living rhythm woven into biology. The robin doesn't preserve coherence in the way a physicist does. She renews it continuously, effortlessly, through the light in her eyes and the chemistry of her cells. This resilience suggests something larger, that life itself might be built to protect and reuse quantum effects. For decades, scientists assumed that the warmth of living systems would destroy any trace of quantum behavior. Yet again and again, we find exceptions. In photosynthesis, in enzymes, in the delicate senses of animals. Wherever life seeks efficiency, it seems to find a way to keep these strange phenomena alive. Perhaps evolution discovered what physics did not, that coherence need not be perfect to be powerful. A robin doesn't need the entanglement in her eyes to last forever. She needs it to last long enough to guide her flight. A leaf doesn't need every excitant to travel flawlessly. It needs just enough of them to keep the plant alive. The quantum world doesn't vanish inside biology. It adapts. It learns to breathe in the same rhythm as life. If you were to look closer at the robin's eye, you would find a shimmering world of molecules moving in concert, electrons shifting, atoms trembling, photons colliding with pigment. It's a place of constant disorder, yet within that disorder patterns emerge. The magnetic field of the Earth passes through her, faint and unseen, but her body feels it as a difference in chemistry, a quiet pull toward the south. Every beat of her heart and flicker of her vision depends on countless quantum events succeeding where they should not. There's something deeply humbling in realizing that life performs such miracles effortlessly, while we, with all our knowledge and machines, struggle to reproduce them. We cool our experiments to freezing temperatures, isolate them from every disturbance, and still lose coherence in a breath. The robin carries hers across oceans. It's a reminder that nature is not an engineer. It's an artist, finding balance in imperfection. You might say that the robin's entanglement survives because it belongs here. Quantum mechanics isn't foreign to life, it is life's native language. The same laws that govern electrons in the vacuum also govern the chemistry of sight, smell, and thought. We are not exceptions to physics. We are its expression, written in the alphabet of molecules. When you hold your hand to the sunlight, you are part of that same conversation. The light that touches your skin was born in a star, travelled across empty space, and entered your body as warmth. Inside you, quantum processes transform it into signals your brain can understand. Sensation, comfort, awareness. You are, in your own way, a creature sustained by entanglement. So perhaps the question is not how the robin keeps her quantum compass alive, but why the rest of the universe finds it so hard to do the same. Maybe what we call fragile is simply what we haven't yet learned to live with. Life, after all, has had billions of years to practice. As the night deepens, the robin's eyes shimmer faintly in the blue light of the moon. Within them, countless pairs of electrons form and dissolve, their brief connections guiding her toward horizons unseen. She will rest soon, but even in sleep the chemistry continues, preparing for the next flight. Her compass is not a device but a conversation, between light and molecule, between order and noise, between what is fleeting and what endures. And as we follow that conversation further, it leads us beyond vision, beyond magnetism, into another sense entirely, one that we often take for granted, yet holds its own kind of quantum music. If sight can hear magnetic whispers, perhaps smell too can listen to vibration. Perhaps the next song in nature's hidden symphony is already floating through the air. After the robin's flight fades into the distance, the night quiets again. The wind softens, and the world feels still enough that even the faintest sensations become noticeable. Somewhere nearby, rain begins to fall. Not a downpour, just a whisper of drops against pine needles. The air cools and thickens, and in that instant you smell it. That unmistakable freshness, part earth, part air, part memory. It's the scent of rain on soil, called petrichor, though the name feels far too scientific for something so gentle. You breathe in, and without trying you're pulled somewhere, perhaps back to childhood, to the first days of spring, to the sound of water sliding down windows. It's one of the quiet miracles of being alive, the ability to recognize invisible things through scent. Yet for all its familiarity, smell is also one of the least understood senses. We know how the eye catches light, how the ear receives sound, but the nose? The nose remains a mystery. How does a handful of drifting molecules conjure entire worlds inside your mind? For a long time, scientists believed they had the answer. They called it the lock and key model. Every odour molecule was thought to have a unique shape, and every receptor in your nose a matching hollow, like puzzle pieces designed to fit. When a molecule with the right shape slipped into its receptor, it would trigger a signal that your brain recognised as a particular smell. The model was elegant, logical, and easy to imagine. It worked well enough to explain why certain shapes resembled others, why some scents seemed related: rose and geranium, orange and lemon. But there were cracks in the theory, faint but persistent. Some pairs of molecules smelled nearly identical even though their shapes were completely different. Benzaldehyde and cyanide, for example, share no real resemblance, yet both smell of almonds. Others, almost twins in shape, could smell utterly distinct. Clearly the nose was doing more than simply matching forms. That puzzle lingered for decades until a few scientists began to ask a more daring question. What if our noses weren't sculptors of shape, but listeners of vibration? What if, instead of feeling molecules, we were hearing them, not with our ears, but with the smallest parts of our cells? Imagine for a moment that every molecule is an instrument, built from atoms bound together by invisible strings. Those strings, the chemical bonds, are not still. They tremble constantly, humming at specific frequencies. A rose petal, a slice of bread, a wisp of smoke. Each carries its own melody of molecular vibration. When those molecules drift into your nose and meet the receptors inside, they don't simply fit, they sing. Inside the lining of your nose lies a field of tiny specialized sensors, millions of them, each one shaped slightly differently, each one tuned to respond to particular frequencies. When a scent molecule lands, electrons within the receptor begin to move. Sometimes, if the vibration of the molecule matches the energy of the receptor, an electron can make a leap. Not a physical jump that you could see, but a quantum one, sliding through an invisible barrier that would normally hold it back. That leap sets off an electrical signal, and your brain interprets it as smell. It's an astonishing thought, that your sense of smell might rely on the same quantum trick that allows a robin to navigate or a particle to pass through a wall. In a way, your nose might be the most musical organ in your body, listening constantly to the microscopic vibrations of the world. You can picture it as a grand concert without sound. Molecules of coffee drift upward from a cup, strings of bonds quivering in thermal motion. Your receptors catch them, one by one, detecting their rhythm. Notes of roasted bean, caramel and smoke combine, forming a chord. Your mind, attuned through experience, translates the frequencies into memory. Morning, warmth, calm. You aren't just smelling, you're recognizing a pattern, replaying a piece of music written in chemistry. There's an elegance to how this explanation ties physics and perception together. Sound, after all, is vibration made audible. Scent might be vibration made tangible. And if that's true, then the air around us is constantly filled with an orchestra of oscillating molecules, each playing its part. Our noses are simply the instruments capable of tuning in. This idea, called the vibrational theory of smell, doesn't reject the old lock and key model entirely. Shape still matters. A receptor has to hold the molecule long enough to sense its music. But once it fits, it's the vibration that completes the song. It's a duet between form and frequency, between geometry and rhythm. The key still fits the lock, but it also hums the right note to open it. When you inhale deeply in a pine forest, what you recognize as pine is really a mixture of resonances, the vibrations of terpenes and resins and other organic molecules, all shimmering at different speeds. The same principle explains why citrus feels bright, why vanilla feels round, why smoke feels sharp. Each vibration enters your body as a tiny pulse of quantum motion. If we could shrink ourselves to the size of an atom and drift inside a single breath, we would see a landscape alive with motion. Molecules spinning, bonds stretching and relaxing like strings being tuned. The air would hum softly, a symphony too high and too fast for ordinary hearing. Your nose, though, is built to catch it. Within its labyrinth of receptors, the world's invisible songs become meaning. The smell of wood after rain, the sweetness of fruit, the trace of perfume on skin. It's strange to think that your memories of people and places, your sense of comfort or longing, could begin with something as small as an electron deciding to move. But that's how the quantum world always touches us. Through decisions so subtle they might as well be whispers. Every inhale is an act of listening. Each molecule that enters your nose carries not just its structure, but its story, how it was shaped by sunlight, air, and time. When you breathe, you join that story. The air that fills your lungs today might contain atoms from ancient forests, from volcanoes, from the breath of creatures long vanished. Smell collapses that history into a single instant, transforming billions of vibrations into a feeling you can name. As you exhale, the melody fades, replaced by the next wave of scents drifting on the breeze. The concert never ends. You're both audience and participant, a living ear in a universe that never stops playing. And if our noses truly listen to molecules, then somewhere beneath that music lies the mechanism itself, a quantum leap, a tiny act of tunneling that turns vibration into awareness. To see how that works, we'll have to follow the electrons a little further into the hidden strings that bind matter to perception, and into the experiment that first proved this silent symphony was real. If smell is a kind of music, then somewhere deep inside the nose there must be musicians, the invisible performers that turn the vibrations of matter into the language of memory. The stage where this concert unfolds is unimaginably small. Each scent molecule that drifts in through your breath is caught by a receptor, a complex of atoms coiled in the lining of your nasal passages. These receptors are not passive. They respond like instruments tuned to particular keys. Some catch low, heavy vibrations like those of musk or earth, while others respond to high, quick tremors like mint or lemon. But the true magic doesn't happen when the molecule merely fits the receptor. It happens when an electron inside the receptor begins to move. It senses that the molecule in front of it is vibrating, and if that vibration happens to match a particular frequency, a sort of microscopic rhythm, the electron can do something almost impossible. It can slip through a barrier it should never cross. It doesn't climb over, it tunnels through. Imagine a dancer performing a leap so perfect that they pass through a wall instead of bouncing off it. In quantum mechanics, this is possible because particles aren't solid dots. They are waves, clouds of possibility. An electron can exist partly on one side of a barrier and partly on the other. If the conditions are just right, if the molecule vibrates in sympathy, the electron's wave flows smoothly across, completing the jump. This leap, though invisible, becomes the spark that triggers a nerve signal to the brain. And that spark, multiplied millions of times, is what we perceive as scent. To picture it another way, you might imagine a guitar string being plucked by invisible fingers. The molecule is the string, the electron is the musician. Each pluck sends a vibration through the receptor, which translates that motion into a pulse of information. The pattern of those pulses forms the melody your brain learns to recognize. Fresh bread, morning coffee, sea air. Each smell is a different tune played by countless electrons moving in harmony. For years, this idea remained just that, an idea. Many scientists were reluctant to believe that living tissue could host quantum tunneling. After all, the process is incredibly delicate. In the controlled environment of a physics lab, researchers must cool particles to near absolute zero to observe tunneling clearly. How could such a thing happen in the warm, messy world of biology? But life, as we've seen before, has a habit of turning the impossible into routine. To test whether our noses truly listen to vibration, a group of researchers designed an experiment so simple it could have come from a fairy tale. They chose a molecule that smells sweet and fruity like orange blossom, pleasant to humans and irresistible to fruit flies. Then they created two versions of it. In one, the hydrogen atoms were ordinary. In the other, every hydrogen atom was replaced with a heavier twin called deuterium, the same element, but with a slightly heavier nucleus. This change doesn't affect the molecule's shape at all. The lock and key theory would predict that both should smell identical. But because deuterium is heavier, its bonds vibrate more slowly, like thicker strings on a cello compared to those of a violin. The scientists then trained fruit flies to avoid the heavy version by pairing it with a mild aversive stimulus. After a short time, the flies learned the difference. When given a choice between the original scent and its deuterated twin, they flocked consistently toward the lighter, sweeter smell. The only difference between the two molecules was their vibration. It was the first real-world sign that tunneling might indeed play a role in smell. This experiment doesn't just prove a theory, it reshapes our understanding of perception itself. It tells us that the nose isn't a mechanical lock waiting for the right key, but a sensitive quantum instrument. It measures rhythm and tone, turning invisible oscillations into conscious experience. Every inhalation becomes a collaboration between physics and feeling, a bridge between the smallest motions in the universe and the deepest memories in the mind. You can feel this bridge in action in the most ordinary moments. When you walk into a bakery, the air is thick with molecules of sugar and yeast and butter, each humming at their own frequencies. Your nose sorts through them instantly, disentangling the chords and layering them into a symphony that your brain names as comfort, hunger, or nostalgia. The same thing happens when you step outside after a storm. The scent of wet soil, petrichor, contains traces of plant oils, ozone, and a compound called geosmin, produced by tiny bacteria in the earth. To your nose, these vibrations form a chord so recognizable that even newborns respond to it with calm. Think of it. Every living creature with a sense of smell is, in some small way, a physicist. Dogs follow trails of scent across miles because their noses can distinguish one molecular vibration from another. Moths find mates through the faintest oscillations carried on the wind. Humans too navigate the invisible, not across continents, but through emotion. The smell of smoke warns of danger. The scent of clean linen feels like safety. The fragrance of a loved one can make time stop. All of it begins with electrons tunneling through molecular walls, playing the world's smallest notes. What's remarkable is how universal this process may be. Quantum tunneling appears in stars, in enzymes, in photosynthesis, and now possibly in smell. Everywhere it shows up, it does the same thing. It allows the universe to cheat a little. Instead of waiting for enough energy to climb over barriers, it simply finds a way to slip through. Life depends on that small act of grace. It's what lets chemical reactions proceed quickly enough to sustain us, what lets photons in leaves find the most efficient path, and what lets scent molecules sing their songs to our consciousness. There's a certain humility in realizing that our ability to perceive beauty, to savor a meal, to breathe in rain, relies on a process too small to see and too fast to imagine. The atoms in our bodies are performing ancient cosmic tricks, bridging gaps that shouldn't be crossable, turning probability into sensation. And maybe that's the point. Life, at every level, is a conversation between certainty and chance. The robin's compass, the leaf's efficiency, the scent of your morning coffee, each is a manifestation of matter's quiet talent for connection. When you next catch a familiar smell, the sweetness of a ripe peach, the smokiness of a candle just extinguished, pause for a moment. Somewhere inside you, electrons are tunneling. Particles are dancing to the vibration of the air. What you experience as scent is, in truth, a kind of listening. The molecules speak, and your body answers. As this realization settles, the story begins to turn inward, because if smell is music, then memory is its echo. The molecules fade, but their vibrations remain within us, translated into emotion. The next part of our journey leads there, to the way scent becomes feeling, and how the smallest quantum notes can awaken the largest memories. The scent reaches you before the thought does. A faint sweetness, mixed with the cool dust of paper, an old book pulled from a shelf after years untouched. The smell is dry and warm at once, carrying hints of wood, ink, and time. You breathe it in, and something inside you stirs. You're no longer in the present moment. You're somewhere else entirely, perhaps in a classroom from childhood, perhaps in your grandmother's house, perhaps sitting under a tree that no longer exists. All of that unfolds within a heartbeat. It happens so naturally that we almost forget how extraordinary it is. A few drifting molecules, invisible and weightless, can summon entire worlds. Scent is memory's shortcut, a direct passage through time that bypasses language and logic. And it's no coincidence that this particular sense feels different from the others. Sight and sound pass through layers of interpretation before they reach emotion, but smell travels straight into the deepest parts of the brain, the limbic system where memory and feeling are born. You could think of it like this. Your nose doesn't just smell, it remembers. It doesn't simply report, it relives. And somewhere beneath that emotional connection lies the same quantum dance we've been following. The subtle tunneling, the vibration, the music of molecules transformed into meaning. Every time a scent molecule enters your nose, it sets off a chain reaction that begins with physics and ends with feeling. Electrons leap, signals fire, and almost instantly, the pattern of that smell, that molecular melody, reaches the amygdala and hippocampus, the regions of your brain that store emotion and memory. There, this smell doesn't just exist, it resonates. It strikes a chord with older experiences, weaving the present with the past in a harmony that no other sense can achieve. That's why the faintest whiff of perfume can stop you mid-step. It isn't the molecule itself that holds power, it's the pattern it awakens. To the brain, every scent is a song, and the first time you smell it, your mind begins composing around it. Years later, when that scent returns, the melody resumes as though it never paused. You don't recall, you rehearse. You feel what you once felt because the same circuits fire again. In this way, the physics of smell becomes the poetry of memory. The vibrations of molecules, tiny and transient, create ripples that reach into who we are. They turn the abstract into the intimate, the universal into the personal. Think of the smell of rain on dry ground, that earthy scent of renewal. The molecules responsible for it are simple, produced by bacteria and plants. But when they reach your nose, they can bring comfort, nostalgia, even a sense of hope. Or the aroma of baking bread. It's just yeast releasing alcohols and aldehydes, yet for many people it means home. These aren't random associations, they're symphonies composed from experience. Each scent that enters your life adds another instrument to your orchestra of memory. There's something almost musical about the way the brain handles this information. When a smell arrives, different regions of the brain activate together, creating chords of association. A single scent might combine warmth, comfort, and sadness, not as separate notes, but as one intertwined emotion. That's why it's so hard to describe smells with words. They don't fit easily into categories. They live in the spaces between feelings. Perhaps this is why smell and music feel so alike. Both rely on vibration, one through air pressure, the other through molecular motion, and both reach the heart before the intellect. A melody and a fragrance can both transport you, even when you don't remember why. You don't need to understand the physics to feel it. It's tempting to think of all this as something purely human, but in truth, it's one of the oldest dialogues on Earth. For animals, smell is survival. It tells them where food lies, where danger hides, where home is. To a dog, the world is made of scents layered in time, each molecule a story waiting to be read. The trail of a friend or foe lingers in the air like written music. Even a bee, finding its flower, navigates by the faint perfume of pollen, a tune played in frequencies far older than thought. In each case, the mechanism is the same. Molecules vibrate, electrons tunnel, signals rise and merge with instinct. Somewhere between motion and meaning, life learns to listen. What's remarkable is how consistent the pattern has been from the start of this journey. In the robin's eye, entangled electrons whisper directions through magnetism. In the leaf, excitons surf the waves of light, finding perfect paths. In the tadpole, protons, tunnel through barriers to create transformation. And here, in the quiet chambers of the human nose, electrons once again leap across invisible gaps to turn vibration into awareness. The physics repeats, but the song changes, from direction to energy, from transformation to memory. When you close your eyes and breathe deeply, every scent becomes a form of time travel. The molecules that reach you might have been released seconds ago or hours ago, yet they carry messages from the past. A candle still warm from flame, a letter folded too long ago, a sweater carrying the faint trace of someone you miss. These are all examples of what the physicist Erwin Schrödinger once called order from disorder. Chaos, in its infinite combinations, creates harmony. The randomness of air becomes the architecture of remembrance. And isn't that what memory is? The mind finding coherence in the noise, the heart finding meaning in the random. The act of remembering is itself quantum-like, fleeting, delicate, probabilistic. Each time you recall something, you don't pull out a fixed recording. You recreate it, slightly different each time, shaped by who you are in that moment. Like entanglement, memory connects distant points in time with invisible threads that ignore distance altogether. Some scientists have even speculated that the brain's ability to form memories might rely, in part, on quantum coherence within its molecular structures, a controversial but intriguing idea. Whether or not that turns out to be true, the metaphor feels fitting. The mind, after all, is the most complex pattern life has ever woven, and the boundary between physics and thought grows thinner the deeper we look. When you inhale the scent of rain, or coffee, or an old book, you are participating in a ritual as old as life itself, the transformation of vibration into experience. The molecules vanish almost as soon as they arrive, but their echoes linger in your mind, folded into the symphony of your being. The smell fades, but the feeling remains, woven into the music of who you are. And as the melody softens, we find ourselves standing again at the edge of water, where another kind of transformation awaits. Because if smell is music, then metamorphosis, the very act of becoming, is choreography. It's matter itself learning to move in ways that seem impossible, and to understand that dance, we'll have to follow the story back to where life's transformations are most visible, to a pond where a small creature is preparing to change everything it knows. The world grows quiet again. Morning mist drifts across a pond, where reeds sway gently, and the air hums with the faint buzz of insects. Beneath the surface, a small shape moves. A tadpole, its translucent body catching the first shards of sunlight that pierce the water. For now, it is simple. A tail for swimming, gills for breathing, eyes like tiny pearls reflecting the sky. But within this fragile body, something miraculous is already unfolding. A transformation so complete that it borders on alchemy. Day by day, the tadpole changes. Its tail begins to shrink, its limbs emerge. The smooth line of its body becomes the shape of a creature that can breathe air and leap onto land. A fish-like life dissolves into an amphibian one. It is not death, and it is not birth. It is something in between, a bridge between worlds, written not in magic but in chemistry. If you were to peer closely, far closer than your eyes could see, you would find that every cell in this tiny body is at work. Enzymes, the molecular artisans of life, are building and unbuilding, cutting and stitching, shaping new tissue from the old. These enzymes are astonishing machines. Each one can speed up a reaction that, left to itself, might take centuries. Without them, life would crawl at the pace of stones. With them, it moves like breath. You can imagine an enzyme as a craftsman with a set of tools. Its structure allows it to hold two molecules in just the right position to help them react. But that explanation, elegant as it sounds, hides a puzzle. The bonds that hold biological molecules together are strong. Too strong, in fact. To break them through ordinary chemical means would require temperatures or energies that would destroy life itself. So how do enzymes do it? How does a tadpole's body dissolve one tissue and form another in perfect harmony, without chaos or harm? If we think only in classical terms, atoms as hard spheres, bonds as solid sticks, the answer seems impossible. But the quantum world, as always, hides a quieter truth. In the invisible depths of the enzyme, particles move like ghosts, slipping through walls that should contain them. The main actors in this invisible play are protons, the positively charged cores of hydrogen atoms, light and restless. In most reactions, a proton must move from one side of a molecule to another to trigger change. But rather than climbing over the energetic barrier that separates those sides, it sometimes takes a shortcut. It tunnels through. Quantum tunneling, in simple terms, is motion without movement. It's as though a traveller faced with a mountain simply fades through it instead of climbing. In the world of particles, this is not fantasy. It is law. Because a proton is not a marble but a wave, it has a certain spread, a probability of being here, and another of being there. If the barrier is thin enough and the energy just right, that probability seeps through, and the proton appears on the far side as if the wall never existed. Inside the tadpole's cells, millions of protons perform this feat each second. As enzymes dismantle one structure and build another, tunneling allows reactions to happen almost instantly. Without it, the metamorphosis would grind to a halt. Bonds would hold too tightly, and the creature's transformation would take not weeks but centuries. The tadpole's body is, quite literally, rewriting itself through the physics of probability. You could say that metamorphosis is a kind of quiet gamble, a collaboration between biology and uncertainty. The enzymes know what to do, but the protons decide how. Each time one tunnels, it collapses a wave of possibilities into a single act, and those acts, multiplied billions of times, become the miracle we see: a tail fading, legs forming, lungs awakening. If you could freeze the process and look at it closely, you might see the tail not simply disappearing, but flowing. Its matter being rearranged rather than destroyed. The molecules that once made the tail are taken apart and used to build new cells, new tissues, new functions. The transformation is almost total, yet nothing is wasted. Nature doesn't discard, it repurposes. Even the old molecules carry whispers of their former selves. It's easy to forget that we too are creatures of continuous metamorphosis. Every breath you take, every heartbeat, every moment of repair or growth relies on these same enzymes, these same quantum leaps. In your body right now, protons are tunneling through molecular walls, making reactions fast enough for life to keep up with time. You're changing at every instant, though so slowly that it feels like stillness. When you think about it this way, metamorphosis stops being a biological curiosity and becomes something universal. The story of all living matter. From tadpole to frog, from seed to tree, from thought to action, everything is in motion, reshaping itself through the quiet permission of quantum physics. The smallest particles in the universe are not content to stay where they are. They slip through boundaries, rewrite connections, and in doing so, they make life possible. It's poetic almost, that the same process responsible for the fusion of atoms inside stars is also what allows a tadpole to grow its legs. In the sun, tunneling lets protons merge, releasing the light that warms Earth. In the pond, tunneling lets protons rearrange, turning one form of life into another. Both are transformations of energy and form, separated by scale but united by principle. If you stand by the water at dusk, you can almost sense that connection. The surface shimmers like liquid glass, reflecting both the sky above and the life below. Somewhere beneath, the tadpole is finishing its transformation. It hovers for a moment, then rises, breaking the surface for the first time. The sound is almost inaudible, a ripple, a breath. but it marks the birth of something new. You could say that the frog climbs from the pond through the same invisible doorways its own atoms have used all along, slipping from one state to another, leaving behind a version of itself but never fully losing it. Each leap across the water mirrors the leaps within its molecules. Life imitates physics without ever knowing its name. In that realization, there's a kind of peace. The boundaries we draw between living and non-living, between past and future, between what is and what could be, are thinner than we imagine. They are membranes, not walls. The frog on the rock, the sunlight on its back, the ripples spreading outward, all of it is one great act of tunneling, a passage from one possibility to the next. And as we linger by the pond, the story begins to widen again, because the same quantum grace that turns a tadpole into a frog also keeps every heartbeat, every breath, every moment of life in motion. The ghost that passes through matter does not vanish when the transformation ends. It continues, weaving through everything that changes, everything that endures. At first light, the pond looks still, as if the night's hush has simply changed colour. But beneath that calm, a restless world continues its work. Molecules drift, collide, and separate. The tadpoles that remain are smaller now, their tails translucent threads disappearing into the water. What looks like stillness is really the aftermath of movement, of billions of reactions so fast, so faint, that they seem to exist between moments. If you could see the world at that scale, the scene would feel almost ghostly. Inside every cell, protons, those tiny fragments of the atom's heart, are moving in ways that seem to defy reason. They slip through the bonds that hold molecules together, cross barriers of energy that should block them, and reappear on the other side as though nothing stood in their way. You might picture them like whispers travelling through walls, leaving no mark but changing everything they touch. Classical chemistry tells us that to move a proton from one place to another, you must push it over a hill of energy. The molecule must gather enough heat or vibration to climb the slope. But in living systems, that climb would take far too long. The hill is steep and the proton is small. Life cannot wait for chance to do the work. Instead, the proton takes a different route. It tunnels. This tunneling is not a journey in the ordinary sense. There's no motion, no path, no climb. The proton simply fades from one side of the barrier and appears on the other. Its wave, the field of probability that describes where it might be, seeps through the wall like light through fog. In human terms, it's like stepping through a locked door without turning the handle. One moment, you're outside. The next, inside. To make this image gentler, imagine two knots in a piece of rope. One knot is tight and resists pulling apart. The other, lighter and looser, begins to slip when pressure is applied. In the microscopic world, tunneling makes every knot behave a little more like the second one. It loosens what should be unbreakable, allowing change to occur without violence. The enzyme that dismantles a molecule doesn't hack at it. It hums softly at the right frequency, and the proton listens. It trembles, hesitates, and then passes through. That moment, that passing through, is what powers nearly everything we know as life. It fuels the transformation of food into energy, the copying of DNA, the repair of tissue, the blinking of your eyes, and the firing of the neurons that let you think. It even drives the fusion reactions that make the stars burn. The same principle connects all of them. The ability of the universe to move forward through impossibly small acts of disappearance. It's strange to think that something so ethereal governs something so solid. A proton has no colour, no surface, no edges. Yet when it tunnels, the macroscopic world changes. The frog's muscles tighten. The leaf turns toward the sun. Your heart beats. You live because particles behave like ghosts. To the human imagination, tunneling sounds like magic. To nature, it is simply efficiency. It's the universe taking the shortest path possible, not by force, but by subtlety. Evolution, it seems, has learned this lesson by heart. Over billions of years, it has shaped molecules and proteins that cradle protons in exactly the right geometries, allowing tunneling to happen with perfect timing. This is why enzymes work so quickly, why they never waste effort. It's as though life has learned to whisper to matter, to coax it into moving without ever pushing. Consider the enzyme catalase, one of the fastest known. Its job is to protect cells from the toxic molecule hydrogen peroxide. Without help, hydrogen peroxide would linger for years before breaking down naturally. But when catalase steps in, the reaction happens in less than 1,000th of a second. In that blink, 2 molecules of hydrogen peroxide become 2 of water and 1 of oxygen, the difference between harm and health. If you were to describe the reaction as an equation, it would read simply 2 parts hydrogen peroxide yield 2 parts water and 1 part oxygen. But the real story happens beneath that line of symbols. In the moment before the change, protons tunnel. Bonds that once held firm begin to fade. The energy barrier dissolves, and then, like breath escaping a sigh, the molecule transforms. You can imagine the cell as a city built from these invisible events. Thousands of reactions per second, each one enabled by a proton's quiet passage. There are no sparks, no cracks of thunder, no drama. Only an endless choreography of vanishing and reappearing, disappearance and return. Every heartbeat, every thought, every leap of the frog on its rock begins in this quiet subatomic theatre. It's humbling, really, to realise that our existence depends not on brute strength, but on gentleness. Life's greatest power lies not in breaking walls, but in passing through them unnoticed. The frog's metamorphosis, your own heartbeat, even the glimmer of stars, all are acts of cooperation between certainty and uncertainty, between what is allowed and what is possible. Sometimes I think of tunneling as the universe's way of forgiving itself. It's as if, hidden beneath every barrier, there's a small kindness, a reminder that not everything must obey the hard edges of logic. Some things are allowed to slip through, and in those slips, existence finds its rhythm. Look again at the pond. The frog, once a tadpole, now sits on a lily pad, motionless except for the slow pulse of its throat. Around it, the air trembles with heat and sound. Beneath, the water glows faintly green with algae, each cell performing its own symphony of quantum leaps. The world seems solid, but at every level it is moving, not outward but inward, through invisible doors. The phrase, protons as phantoms, may sound poetic, but it is also literal. They are the wanderers that refuse to be trapped, and yet their journeys give shape to everything we know. They pass unseen through the fabric of matter, connecting the improbable with the inevitable. Without them, the sun would stop shining, the pond would freeze in darkness, and the frog would never draw its first breath. And so the story continues, from invisible phantoms to visible motion, from the whisper of tunneling to the living machinery it powers, because the ghost within transformation does not end with enzymes or frogs. It reaches out into every form of metabolism, into the pulse of energy itself, where quantum tunneling turns chaos into order and breath into life. By now, the sun has risen fully above the pond, scattering light over the water until it shimmers like a living mirror. The frog sits on a flat stone, perfectly still except for the slow pulse beneath its throat. Around it, the reeds sway in rhythm with the breeze. On the surface, everything seems complete, the metamorphosis finished, the story told. But deep inside the frog, within every cell, the work continues. Transformation never really ends. Life is not a single change, but a continuous unfolding, an unending dance of chemistry, energy, and time. If we could shrink ourselves and wander inside one of those cells, we'd find a world busier than any city. Molecules rush like commuters, enzymes work like artisans, and energy flows like traffic through invisible streets. At the heart of this city are the same quantum tricks that shape the tadpole's transformation: the tunneling of protons, the reshaping of bonds, the graceful passing of particles through barriers they shouldn't cross. The difference is scale. Now, instead of one creature changing form, these tiny acts sustain every living heartbeat on Earth. In this invisible machinery, enzymes act like tireless builders. Each one is designed, or more truthfully evolved, to perform a specific task. Some snip large molecules into smaller ones so that energy can be released. Others weave smaller pieces back together into the structures of muscles, nerves, or skin. These are not random interactions. They happen with astonishing precision. In the time it takes you to blink, trillions of reactions occur in your body. Each one depends on the same principle we've already met: a proton that doesn't wait to climb the mountain of energy before it, but slips quietly through. Take, for example, one of nature's simplest yet most astonishing reactions: the breakdown of hydrogen peroxide. It's a byproduct of life, formed naturally inside our cells, but left alone, it would linger dangerously. The molecule wants to become harmless, to turn into water and oxygen, but that transition, without help, would take years. Then along comes an enzyme named catalase. Its structure is like a careful cradle, holding the hydrogen peroxide in just the right shape. When the time comes, the bonds inside the molecule tremble, and protons tunnel through barriers that should stop them. The change happens in less than a heartbeat, so fast that it's almost outside of time. 2 molecules of hydrogen peroxide become 2 of water and 1 of oxygen, and the cell is safe again. It's a simple reaction on paper, but in feeling, it's a small act of mercy. Something dangerous transformed into something gentle, not by destruction, but by rearrangement. When you breathe, that oxygen you draw in carries the quiet record of countless such acts. The air that fills your lungs is built from the same subtle chemistry that keeps the frog's heart beating, that turns sunlight into sugar in the leaves above you. This pattern, the use of tunneling to speed change, is everywhere. In your stomach, enzymes work to break food into energy. In your muscles, molecules release that energy again as movement. In plants, electrons leap between pigments to capture light. In the soil, bacteria perform reactions that turn death back into nourishment. Each of these is the same story told in a different accent. Matter rearranging itself with impossible grace, finding the shortest path between what is and what could be. If the universe were left to classical physics alone, these processes would crawl. The energy barriers would be too high, the reactions too slow, but life doesn't wait. It uses the quantum world's generosity, its willingness to bend, to allow for the improbable. That generosity is why you can think, breathe, and dream. Every heartbeat, every flash of thought, every glint of movement in the frog's eye is powered by particles choosing over and over to take the impossible route. You could say that life is a weaver, and tunneling is the thread it uses. Each enzyme, each reaction, is a loom where matter is pulled apart and rewoven in new shapes. Nothing is lost, only rephrased. Hydrogen becomes water, carbon becomes sugar, oxygen becomes breath. The weave tightens and loosens over and over, forming the fabric of everything alive. If you could hear it, it would sound like a soft rustle, a universe-sized whisper repeating the same rhythm: connect, release, connect again. There's something deeply comforting in that rhythm. It means that even decay is not an ending, only a return to the pattern. The energy that fades from one form reappears in another. The molecules that dissolve in one body become part of another's growth. You're made of things that once belonged to oceans, mountains, trees, and stars. And through the machinery of change, those same atoms are always finding new combinations, new meanings. Some scientists describe this with the language of efficiency. They say tunneling makes life more energetically favourable, but in the soft language of nature it feels more like kindness, a cooperation between the smallest and the largest scales. The frog, the forest, the air, and even the starlight that reaches the pond are all part of one continuous metabolism, powered by the universe's ability to let go of impossibility. You could almost imagine the Earth as one vast living enzyme. The oceans mix and dissolve, the atmosphere breathes, the crust melts and reforms. Protons tunnel, elements merge and separate. From the smallest cell to the movement of continents, everything participates in this same grand choreography. Change without chaos, motion without destruction. When you pause and take a slow breath, that simple act connects you to all of it. The air you inhale is not just oxygen, it's the memory of transformations. It has passed through leaves, through lungs, through the cells of creatures long vanished. Every particle you breathe has tunneled, reacted, and rearranged countless times since the beginning of time. Each breath is proof that change, however invisible, is eternal. As you exhale, a small ripple of warmth leaves you, rising into the morning air. Perhaps it will be drawn into the next leaf, or into the surface of a distant wave. The energy you release will not vanish. It will find new form as it always has. The machinery of change never stops. It simply shifts its attention, flowing from one story to another, from one body to the next. And as you watch the frog leap into the water, a single splash sending circles across the pond, you can see the same principle at work. The circles expand, overlap, fade, and are reborn in others. Nothing ends, everything continues. It's the same lesson written in every atom, that life persists not through permanence, but through motion. Somewhere deep within that movement, the quantum whispers go on. Protons tunneling, bonds trembling, molecules changing hands. The invisible keeps the visible alive. And as we follow that current forward, the story will lead us upward once again, to the leaves that catch the light, to the way sunlight becomes sugar, to the greatest act of energy translation on Earth. Somewhere deep within the heart of the sun, where matter folds into light and pressure becomes nearly infinite, a single photon is born. It emerges from fusion, that ancient dance where atoms of hydrogen combine to form helium, releasing tiny sparks of energy. Each spark is small, but together they create the glow that sustains every living thing on Earth. The photon begins its journey in darkness, surrounded by unimaginable heat and density. It moves no faster than light itself. Yet in those depths, progress is slow. The sun's interior is so thick that each photon collides, scatters and bounces for thousands of years before it finally finds its way to the surface. When at last it escapes into space, it races freely at nearly 300,000 kilometers per second, the universe's ultimate speed. The vacuum offers no resistance, no sound, no touch. It will never tire. In just over 8 minutes, it will travel 93 million miles to reach a small blue planet spinning quietly around its star. From the photon's perspective, time hardly exists. The journey is instantaneous. One moment inside the star, the next in the thin breath of Earth's atmosphere. Down below, morning begins. A leaf trembles slightly in the wind. On its surface, millions of cells wait with open hands, molecular nets of green pigment ready to catch the first light. And then it happens. The photon strikes. No explosion, no spark, just absorption. It vanishes into a molecule of chlorophyll, its energy transferred perfectly, as if it had always belonged there. What began as a fusion flame inside a star becomes a quiet pulse of life inside a leaf. Photosynthesis has begun. The word itself sounds clinical, but the process is nothing less than a miracle written in physics. It means putting together with light, and that's exactly what plants do. They take sunlight, water and carbon dioxide and transform them into sugar and oxygen. Out of radiance, they make nourishment. Out of thin air, they make the breath of worlds. The reaction is both ancient and precise. Each molecule of chlorophyll captures sunlight not as heat, but as information, the rhythm of energy itself. The photon's arrival excites one of its electrons, lifting it to a higher energy state, as if struck by inspiration. That energy, delicate and fleeting, must then be carried to a special chamber inside the cell, the reaction center, where it can be stored and converted. You can imagine it as a journey through a microscopic forest of molecules, each one poised to receive the passing spark. In a purely random world, that energy would bounce from molecule to molecule like a traveller lost in fog, losing direction with each step until the light faded as waste heat. But that isn't what happens. The transfer is almost perfect. In many plants and bacteria, more than 95% of the light's energy reaches its destination intact. Almost nothing wasted, almost nothing lost. To grasp the scale of this perfection, imagine tossing a ball through a dense crowd and having it land precisely in one person's hands every single time. The odds defy logic, yet the leaf does it, effortlessly, millions of times per second across forests and oceans for billions of years. Somewhere within this green machinery lies a secret, a principle of order that lets chaos produce harmony. Every second, more than 1 trillion photons strike every square metre of the planet's surface. Some bounce away, some warm the air, but countless others are caught by leaves, algae and bacteria. The result is astonishing. A planet continually rebuilding itself from light. The sugars created through photosynthesis feed not only the plants that make them, but everything that eats those plants, and everything that eats the eaters. The oxygen released fills the atmosphere, turning an inhospitable rock into a world where breath can exist. All of this happens because of the photon's long journey, because light itself decided to take part in life. If you listen carefully, you might feel the rhythm of this exchange. The sun gives, the earth receives, the photon falls, the leaf catches. The process is so constant that we stop noticing it, yet it is the quiet foundation of all we are. Each cell in your body, each thought in your mind, is powered by energy that once travelled across space as light. You are, in a very literal sense, woven from sunshine. When we speak of photosynthesis, it's tempting to think only of plants, of forests and gardens and grass. But in truth, this process reaches far deeper. Long before trees shaded the earth, ancient bacteria were already using light to live. They discovered how to catch photons and turn their energy into chemical bonds, into storage, into survival. The descendants of those bacteria still dwell inside every green cell today, tiny witnesses to the first conversations between light and life. There's a tenderness in knowing that each leaf is both ancient and new, carrying within it the memory of the first dawn. When you hold a leaf to the sun, you're watching the continuation of a dialogue that began more than 3 billion years ago, a dialogue in which the universe began to recognize itself. The light that left the sun 8 minutes ago meets the descendants of starlight from eons past. The exchange is complete, energy returning to its source in a new form, alive. At night, when the stars appear, it's easy to feel small. But if you think of that single photon's journey, the scale changes. You realize that distance means little to light. The same force that shines from the heart of a star now rests quietly in the food you eat, the warmth in your breath, the glow of thought behind your eyes. The boundary between the cosmic and the personal disappears. The photon has travelled nearly 100 million miles, only to find peace inside a leaf no wider than your hand. There, it will begin a new journey, not through space, but through matter. its energy will weave through molecules, find the fastest path to the reaction center, and transform again into the currency of life. This is where our story turns inward, into the green maze hidden within each leaf, where sunlight learns to think and where the universe performs its quietest miracle, turning radiance into growth. If you could shrink yourself down to the scale of a single cell in that leaf, smaller than dust, smaller than the wavelength of light itself, you would find yourself in a landscape unlike anything you've ever imagined. It is not a forest of wood and bark, but a forest of green molecules suspended in liquid crystal. Every surface glows faintly with captured sunlight. Every vibration carries meaning. This is the heart of photosynthesis, the green maze through which the sun's gift must travel. When the photon's energy first touches a chlorophyll molecule, it doesn't become heat or vanish into brightness. Instead, it awakens an electron inside, lifting it to a higher state of energy. But that electron cannot stay where it is. It is restless. It passes its energy to the neighbouring molecule not as a charge but as a ripple, a small packet of light energy known as an exciton. You can imagine this exciton as a tiny traveller made of sunlight, carrying the photon's memory on its back. It doesn't move alone. It moves as a shared pulse of energy through a crowd of pigments, each molecule passing it along to the next like a relay runner handing off a torch. The goal is simple. Reach the reaction center, a small chamber buried within the cell, where the energy will be converted into chemical bonds, the lasting form of life's fuel. But the path is far from simple. The inside of a chloroplast, the structure where all this takes place, is crowded and complex, a maze of proteins and pigments arranged in networks so dense that the exciton faces endless choices. It can go left or right, up or down, backward or forward. A random journey would be terribly inefficient, like trying to find a single door in a city without a map. Every step risks losing energy as heat. Yet somehow, the exciton never seems to lose its way. For decades, scientists tried to explain this impossible precision. They pictured the exciton as a bouncing ball, ricocheting from molecule to molecule until it happened upon the right one. But that picture didn't fit the data. The reactions were too fast, far faster than any random hopping could account for, and almost no energy was wasted. Something was guiding the exciton, something unseen but deeply ordered. To grasp how extraordinary this is, think about the scale. Inside 1 square millimetre of leaf tissue, there are hundreds of thousands of chloroplasts, each containing millions of chlorophyll molecules. Together, they form a network so intricate that the photon's energy could take countless possible paths. Yet, within less than a billionth of a second, that energy always finds the shortest route to the reaction center. It's as if the exciton already knows the answer before the question is asked, as if it senses the geometry of the entire maze at once. In human terms, it's like walking through a labyrinth blindfolded and reaching the exit on your very first try. No missteps, no hesitation, just perfect intuition. How can nature do this? The answer once again lies in the strange laws of the quantum world. In our everyday experience, an object must choose one path at a time, but in the quantum realm, particles can explore all paths simultaneously. The exciton doesn't pick a single road, it takes them all. It spreads out like a wave, exploring every possible route through the network of molecules at once, and interferes with itself along the way. The longer routes cancel out, while the most efficient path strengthens. When the wave collapses, the energy arrives exactly where it needs to be, almost as if guided by foresight. Though we'll explore this deeper in the next session, this idea, quantum coherence, is the thread that ties it all together. It means that even inside the warmth and motion of a living leaf, the energy of light behaves like a symphony rather than a collision. The pigments don't compete for the photon's gift, they share it, their vibrations weaving together into one unified song. If you could translate that song into sound, it might resemble 1,000 tuning forks humming in harmony. Each chlorophyll molecule vibrates slightly differently, yet they remain linked through the shared wave of the exciton. Every vibration nudges the energy forward, closer to the reaction center, never wasting a note. The process is so elegant that some physicists have compared it to a quantum computer, an organic system capable of evaluating every route simultaneously and choosing the best one, effortlessly, in the blink of an eye. But the most beautiful part is that the system doesn't need perfection. It works within noise, within warmth, within imperfection. In the lab, scientists must cool quantum systems to near absolute zero to keep them coherent. But nature somehow achieves the same trick at room temperature, or even in the heat of tropical sun. The molecules in the leaf are not still, they tremble and sway. Yet instead of destroying the order, that trembling helps maintain it, like a gentle breeze keeping a flame alive instead of blowing it out. This balance between order and chaos, between fragility and resilience, seems to be the signature of life itself. Too much stillness, and nothing moves. Too much noise, and everything falls apart. But here, in the maze of green, the two coexist perfectly. The exciton's wave moves through disorder not despite it, but because of it. Life doesn't fight chaos, it uses it. You can almost feel this balance when you stand under a tree and look up through its canopy. The sunlight filters through countless leaves, each one performing this dance silently and tirelessly. The energy that will one day feed you, clothe you, or fill your lungs is, at this very moment, racing through molecular mazes in patterns more precise than any human-made system. A forest may seem passive, a still collection of trunks and leaves, but it is anything but still. Every second, billions of photons are entering, their energy flowing through chlorophyll, forming sugars, releasing oxygen. The trees are thinking in their own way, calculating, solving, converting light into life with precision no machine can match. And to think, it all begins with that first step, the moment a single photon becomes an exciton, a tiny traveller wandering through the green labyrinth of the cell, guided by rules older than the stars. As we drift further into this story, we'll follow that traveller more closely. We'll see how the exciton's path, though invisible, is shaped by the same quantum logic that allows particles to exist in many states at once. What seems like intuition is really superposition, the wave that finds its way. Imagine standing in a sunlit meadow where the leaves shimmer as the wind moves through them. To your eyes, it's a peaceful scene. Sunlight drifting lazily through green. But if you could shrink down again to the scale of molecules, you would find that same light racing in a hidden ballet. Deep inside every leaf, the energy from each photon is not just moving, it is exploring, dreaming, deciding. It is doing something that seems almost impossible, finding its way through chaos by becoming many things at once. When scientists first studied how photosynthesis works at the atomic level, they discovered something so unexpected that it felt almost poetic. The exciton, that small packet of sunlight energy born when the photon strikes chlorophyll, does not behave like a simple traveller. It doesn't stumble blindly through the green maze, bouncing from one molecule to another until it finds the right destination. Instead, it becomes a wave, spreading across multiple molecules at the same time. To understand this, you might imagine a traveller standing at the entrance of a vast labyrinth. In the ordinary world, they would take one path, make a turn, reach a dead end, and try again, losing time with every wrong step. But the exciton is not bound by ordinary rules. It divides into countless versions of itself, 1,000 travellers walking 1,000 paths simultaneously. Some hit walls, some wander in circles, and some find the centre. When the wave finally collapses, all those paths merge again, and the energy appears exactly where it's needed, at the reaction center. This strange ability comes from a property called quantum coherence. It means that the particles in the system are connected in such a way that they share information instantly. The excitons wave doesn't simply move, it feels the entire network of chlorophyll molecules as one continuous space. It doesn't guess the right path, it senses it, as if the leaf itself were guiding it through a conversation of vibration and rhythm. You can think of coherence as harmony. When a choir sings perfectly in tune, each voice resonates with every other. The sound waves combine, amplifying the melody and cancelling out discord. The same happens in a leaf. The molecules vibrate together, aligning their rhythms so that the energy flows in the most efficient way possible. The excitons wave interferes with itself. Destructive interference erases the paths that waste energy. Constructive interference strengthens the best ones. In this way, the leaf performs a calculation, a natural algorithm that finds the fastest route for light to become life. To some, this might sound abstract, but nature gives us a hint. A similar experiment has been performed in the laboratory with a pigment protein complex from a simple, photosynthetic bacterium known as the Fenner-Matthews-Olson complex, or FMO for short. Scientists used pulses of ultra-fast laser light to observe how energy moved through it. To their astonishment, they found that the energy didn't hop randomly between molecules. Instead, it oscillated back and forth in rhythmic waves that lasted far longer than anyone thought possible. Coherent waves, moving together even in the warmth of a living cell. That experiment was a revelation. It showed that the same laws we study in quantum optics, the delicate superpositions that usually require cold, controlled lab conditions, are at play inside the cells of everyday plants and bacteria. The leaf is, in a quiet and humble way, a quantum device. It takes the chaos of sunlight and turns it into an organized flow of energy. It doesn't freeze out the noise of the world, it collaborates with it. This cooperation between order and disorder is perhaps the most astonishing part of all. In physics, we often think of noise as an enemy, a force that destroys coherence. But life seems to use it like a sculptor uses clay. The slight vibrations of the surrounding molecules don't break the pattern, they refresh it. When the excitons wave begins to lose its rhythm, those molecular tremors nudge it back on beat, allowing it to continue exploring all possible paths. It's as if the leaf breathes life into the wave, keeping it alive just long enough to finish its journey. There's something deeply comforting in that, the idea that chaos, when embraced gently, becomes a source of stability. The leaf doesn't fight disorder, it dances with it. It listens to the hum of thermal motion and turns it into part of the song. The excitons coherence may only last for a few trillionths of a second, but within that brief eternity, it performs a calculation so perfect that almost no energy is lost. If you could see this from within, it would look like a ripple of light weaving through a web of green jewels, the pigments shining, pulsing, resonating with each other. The wave would shimmer, split, and recombine, like sunlight reflecting off the surface of water. Each interference pattern would represent a choice made by the universe itself, an optimization so natural that no consciousness is required, only the laws of physics, written elegantly in the structure of life. And yet, there is a kind of consciousness here in the broader sense. Not thought or intention, but awareness. The system knows itself. Each molecule responds to its neighbours. The network acts as one. The leaf, in its own wordless way, thinks, not in ideas or symbols, but in relationships of energy and motion. Light enters, order emerges, and the boundary between physics and biology blurs completely. When the excitons wave finally reaches the reaction centre, the energy is captured and stored in chemical bonds. In that instant, the photon's long journey ends. It has travelled from the core of the sun to the heart of a leaf, passing through space, air, and quantum uncertainty, only to rest as sugar, the simplest, sweetest form of energy. And as we step back from this microscopic stage, the implications ripple outward. Every tree, every blade of grass, every algae bloom in the ocean performs this same miracle endlessly. Billions of excitons, billions of coherent waves exploring, finding, merging, all in service of one act, transforming light into life. The next time sunlight touches your skin, consider that it's not merely warmth. It's a memory of waves finding their way, of light solving problems faster than thought. The forest around you, the fields, the food on your table, all of it owes its existence to the quantum logic of coherence, to the wave that never gets lost. And as we leave the leaf behind, we'll follow that light upward again to where forests breathe and grow together, where the quantum ballet becomes not just a microscopic story, but a planetary one. Somewhere beyond the single leaf, beyond the tiny waves and pigments we've been following, an entire world is breathing. A forest, vast and calm, stretches out beneath a sun that has been shining for 4.5 billion years. Each tree sways gently in the wind, each branch alive with movement so subtle that we almost never notice. But beneath this quiet, something extraordinary is happening. A planetary symphony of light and chemistry, of quantum rhythms scaled up to the size of continents. The forest is not silent. It hums, not with sound, but with energy. Every second, billions of photons arrive from the sun, washing across leaves, grass, moss, and water. In those moments, the same miracle we saw within a single leaf repeats everywhere. Photons become excitons, excitons become sugar, sugar becomes motion, breath, life. It happens in every green thing, from the tallest cedar to the smallest blade of grass, a choreography so complete that it sustains everything we know. If you could step back far enough, if you could somehow see energy instead of colour, the Earth would appear as a shimmering green halo. Light continuously entering, transforming, and radiating back out as heat, movement, and oxygen. Each tree would glow softly, each ocean bloom would flicker, each field would shimmer like a sea of tiny lanterns. The whole biosphere is a vast interlinked network of quantum activity, a living web that turns sunlight into matter with near-perfect efficiency. The numbers are beyond imagining, but we can translate them into something that feels human. Every heartbeat of the planet, every second that passes, roughly 16,000 tons of new green material rise into existence. That's the weight of a mountain of life created every heartbeat, simply by light finding its way through leaves. Forests, fields, and algae all perform this feat quietly, tirelessly, without noise or machinery. Each one runs on the same invisible mathematics, on coherence and vibration, on the soft logic of photons and protons working together. It is easy to think of trees as passive things, as backdrops to our lives rather than living beings with their own purpose. But the truth is that a forest is not just alive, it is aware in its own steady way. Through networks of roots and fungi beneath the soil, trees share sugars, signals, and warnings. The carbon they make from light travels between them like a conversation, one species feeding another. The air they exhale becomes the air we breathe, and what we release returns to them. The exchange never stops. It's a dialogue written in the language of chemistry, yet orchestrated by the physics of light. If we could hear that conversation translated into sound, it might resemble a slow, continuous tone, the hum of life itself. It would rise with the day, fade with the night, and pulse with the seasons. In spring, the melody would brighten as leaves unfold and photosynthesis awakens. In autumn, it would soften, the notes drifting into quiet as sunlight weakens and the trees rest. The music of the forest is not heard but lived. It flows through everything that breathes. What makes this even more astonishing is that the forest does not waste. Nearly every photon that enters a leaf finds a purpose. The light that isn't used for energy becomes warmth. The warmth stirs the air. The moving air feeds clouds and rain. Even the shadows beneath the canopy, the dim places where almost no direct light reaches, are part of the cycle. Ferns, fungi, and mosses harvest what little energy remains, completing the circuit. Nothing is idle. The physics that began in a single chlorophyll molecule scales upward into an entire ecosystem, into a planet that self-regulates through balance and feedback. There's a phrase often used by physicists to describe coherence. They call it phase harmony. It's a technical term, but it sounds almost poetic. It means that the waves within a system move together, their peaks and troughs aligning in rhythm. On a planetary scale, that's what life is. Phase harmony. Each cell, each leaf, each creature vibrating in time with sunlight, exchanging energy in perfect synchronization. When you walk through a forest, you're walking through a quantum field scaled to human size. The warmth you feel on your skin, the oxygen filling your lungs, the ground steady beneath your feet. All of it exists because light learned to cooperate with matter. It is a relationship older than breath, older than thought. Every tree is a bridge between the stars and the soil, between energy and form. Sometimes when wind moves through leaves, you can hear a sound like breathing. The canopy exhales, the trunks respond, the ground absorbs and releases. The air tastes faintly of sweetness, oxygen mixed with moisture and dust. That sweetness is the trace of photosynthesis, of photons reborn as sugar. You are, in that moment, inhaling the work of light. The forest doesn't just provide air, it creates memory. Every breath you take carries a tiny record of sunlight's journey, from the heart of the sun, through the void, into a leaf, through countless molecular dances, and finally into you. In that way, you and the forest are inseparable. The energy that once existed as light within a star now flows through your cells, allowing your eyes to see the very sunlight that birthed it. When you exhale, the carbon you release becomes part of the forest again, returning to the trees that will transform it once more into life. The cycle is complete, endless, effortless. It's easy to feel small beneath the canopy, but perhaps the truer perspective is not smallness, but connection. The same wave that found its way through the maze of chlorophyll also finds its way through you. In the glucose in your blood, in the rhythm of your breath, in the warmth of your skin. The forest is not something apart from you. It is the continuation of the same process that began when the first photon left the sun. When night comes and the forest falls into shadow, the light doesn't vanish, it rests. The trees slow their rhythm, the flow of sugars eases, the air cools. But even in the dark, life continues quietly. Respiration replacing photosynthesis, energy flowing in reverse, feeding the roots, preparing for dawn. The cycle is not paused, only inverted. Every leaf carries the memory of light, waiting for morning to return. And when it does, the forest will awaken once more, each leaf ready to catch another photon, another spark of ancient sunlight. The same wave that has been travelling since the dawn of time will meet the same molecules and begin again, effortlessly. In that endless repetition lies the secret of survival. Life endures not by resisting change, but by transforming it, by letting light think through matter. Every forest, every field, every green thread of algae in the sea is a quantum computer made of leaves, solving the problem of existence at the speed of light. And as this great green machine hums softly across the planet, It prepares the stage for the next act of the story, one not about survival, but about transformation. Because the same quantum logic that moves light through leaves also moves change through genes. The physics that guides a photon through a maze will, in time, guide evolution itself. The rain has passed, leaving the air cool and bright. Somewhere on a damp stone, a snail moves slowly, tracing a glistening path behind it. Its pace is almost meditative, unhurried by the rush of the world around it. The spiral of its shell glows faintly in the wet light, a perfect curve, ancient and mathematical, echoing the same geometry found in galaxies and hurricanes. You could stare at it for hours and still feel you hadn't quite understood how such beauty could come from simplicity. Yet this spiral, like the leaf or the photon, carries the story of physics and life working together, the story of evolution itself. Charles Darwin once called evolution the grandeur in this view of life. The idea that from simple beginnings, endless forms most beautiful and most wonderful have evolved and continue to evolve. It is a slow, patient process, written not in years, but in eons. It explains why the snail's shell matches the colour of the stone beneath it, why a frog's skin blends with a pond's edge, why a robin's egg is blue. Life adapts, generation after generation, refining itself to fit the shifting world. At the heart of this idea lies a kind of quiet logic. Variations appear, small differences between individuals. Those differences that help survival are passed on, those that don't are quietly erased by time. The process needs no direction, no designer. It is nature's endless experiment, guided by feedback alone. But behind that familiar explanation hides a deeper question, one that even Darwin could not answer. Where do those first variations come from? What sparks the small random changes that become the raw material for evolution? To understand this, let's return to the snail. Its shell, though simple to the eye, is built by instructions encoded in its DNA. Long molecules that coil like music written on ribbons. Each tiny cell in the snail's body reads a part of that score, building proteins, forming pigments, shaping the spiral. Sometimes, however, a note in the music changes. A single letter in the genetic alphabet, one base out of billions, shifts. Maybe a bond breaks differently, maybe an atom moves where it shouldn't, maybe a proton tunnels across a barrier it was never meant to cross. That single change can alter the pattern of pigment, the curl of a shell, the strength of a limb. Over generations, these small, invisible shifts accumulate, turning possibility into diversity. In Darwin's time, the word mutation didn't yet exist. He described variations as chance differences. Today we know that they arise from the physics of the molecular world, but even now the source of that chance remains mysterious. Why should atoms sometimes behave one way and sometimes another? Why should nature's code, usually so faithful, occasionally make an error that leads to a new trait, a new species, a new world? To see how deep this mystery runs, imagine watching a DNA molecule unwind during replication. The double helix splits in two, each strand serving as a template for its mirror image. At each step, molecules called bases, adenine, thymine, cytosine, and guanine, line up and pair with their partners. It's an exquisite dance of precision, each base recognizing the one it belongs with. And yet, every so often, something slips. A single base pairs with the wrong partner. The error might be small, just one mismatched letter, but it changes everything that follows. Most of the time, such mistakes are repaired, corrected by the cell's meticulous editing machinery. But occasionally, one escapes. The result is a mutation, a tiny deviation in the code. And while most mutations are neutral or harmful, some bring unexpected advantages. A better camouflage, a stronger shell, a sharper eye. Life, in this way, learns from its own accidents. But what if those accidents aren't purely random? What if buried beneath the surface of biology, the same quantum processes we've seen in light and enzymes are quietly shaping evolution too? After all, DNA is a physical object built from atoms, governed by the same laws that allow protons to tunnel and electrons to entangle. Perhaps the randomness we call mutation is really the echo of quantum uncertainty, a roll of the universe's smallest dice. Consider the colours of the snail's shell. In one environment, the pattern might make it invisible to predators. In another, the same pattern might make it stand out, easier to find. Over generations, the individuals with the better camouflage survive, passing their pattern to their offspring. But the first change, the shift that altered the pigment's arrangement, began at the molecular level, where a single atom in a gene behaved differently from the rest. At that moment, quantum chance met natural selection. If you hold the snail shell in your hand, you can feel how time has been carved into its form. Each spiral is a record of growth, of survival, of trial and error. You can think of it as a fossilized echo of quantum events, the macroscopic outcome of microscopic uncertainty. Every life form carries such echoes. The pattern on a butterfly's wing, the shape of a leaf, the song of a bird. All are outcomes of small quantum deviations that found their way into permanence. This isn't to say that evolution abandons randomness. On the contrary, it depends on it. Without the gentle unpredictability of the quantum world, life would be static, frozen in one form forever. But because matter itself is restless, capable of tunneling, vibrating, and existing in many states at once, life can explore possibility. It can innovate without knowing it. The universe, through biology, experiments with itself. The next time you see a snail inching across a path, consider how much of the universe is contained in its slow movement. The atoms in its shell were once part of stars. The pattern of its spiral was shaped by both genetic code and cosmic probability. It is not a creature apart from physics, but a continuation of it. A system of molecules guided by the same invisible principles that govern light and gravity. Darwin wrote that nature's grandeur lies in its endless forms most beautiful. He was right. But we might add one more line, that those endless forms are born from endless uncertainty. Every living thing is, in its own quiet way, an expression of quantum chance, a reminder that from the smallest tremors of matter, beauty can emerge. And as we watch that snail disappear into the grass, the question deepens. If the spark of variation begins at the quantum level, what happens inside the molecule that makes it so? How does the code of life, that double helix, hold the possibility of both perfection and error within its delicate structure? To find that answer, we'll need to look closer into the spiral itself and see what dances beneath the surface of the DNA. To understand how life remembers itself, you must go smaller than a cell, smaller than the molecules that make up a shell or a leaf. You must enter the spiral, the quiet vault of memory carried inside every living thing. Here, in the dim shimmer of atoms, rests the most elegant structure ever discovered, the double helix of DNA. At first glance, DNA seems impossibly simple. Two ribbons winding around each other like intertwined melodies, endlessly repeating. But within those strands lies the entire story of a being, how it grows, how it breathes, how it repairs, how it becomes what it is meant to be. The code is written in an alphabet of 4 chemical bases: adenine, thymine, cytosine, and guanine, letters that pair together in perfect symmetry. Adenine always joins thymine, cytosine always pairs with guanine. Together they form the rungs of the molecular ladder, tiny bridges between the spiraling rails of sugar and phosphate that give the helix its backbone. You could think of it as a song written on an infinite ribbon, each base a note, each sequence a phrase. When played, the music becomes life. And yet, like any great song, It is never performed exactly the same way twice. Each time DNA is copied, small variations arise, and from those variations, evolution composes its endless harmonies. The structure itself is a marvel of balance. It must be strong enough to endure for a lifetime, yet flexible enough to unwind whenever a cell divides. It must guard its information fiercely, yet allow change, because without change, life would stop evolving. The double helix achieves all this by using the chemistry of bonds, delicate attractions between atoms that are just strong enough to hold, but just weak enough to break when needed. And within those bonds, hidden from sight, the quantum world hums softly. Every link between the base pairs is held together by protons, tiny particles that bridge the two strands like pins in a zipper. Normally, each proton stays where it belongs, locked in place by the geometry of the molecule. But in the mysterious way of quantum particles, a proton isn't truly fixed. It exists as a blur, a wave spread across two possible positions. Most of the time it stays put, but sometimes it tunnels. It appears on the other side of the bond, briefly shifting the pairing between the bases. Adenine no longer fits perfectly with thymine, guanine no longer matches cytosine. The code flickers. This flicker is fleeting. The proton often returns to its original place within a trillionth of a second. But if the DNA is being copied at that moment, the shift can be frozen into permanence. The cell reads the temporary mispair as truth, and a new base is inserted where the old one should have been. A mutation is born. It's a tiny act, invisible, silent, and yet it can change everything. One misplaced base in a billion might give a butterfly a new pattern, or a flower a new colour, or a creature a slightly sharper sense of smell. Most changes do nothing. Some break the rhythm. But once in a while, one note transforms the entire song. There's a quiet humility in realising that life's creativity depends on imperfection. The very structure designed to preserve information, to copy it faithfully, generation after generation, also contains the seeds of its own revision. It's as if nature built a whisper of uncertainty into its most sacred code, a reminder that no perfection lasts forever. The physicist Erwin Schrödinger once wondered what kind of molecule could carry the complexity of living information. He called it an aperiodic crystal, a structure ordered enough to store data yet irregular enough to allow for variety. When DNA was discovered years later, it fit his vision exactly. But what he could not have known was how deeply quantum mechanics would be woven into its behaviour. Within each bond, protons are constantly choosing, or more accurately, existing between choices, their blurred presence making the molecule both stable and fluid at once. If you could zoom in close enough to see it, DNA would not look like a static ladder. It would shimmer like a ribbon of light, twisting, vibrating, shifting. Its bonds would pulse with probability. Each moment the molecule would be slightly different from the one before, an ever-changing landscape of motion. Yet out of that motion emerges constancy. The information persists even as the atoms dance. That balance between chaos and structure, randomness and order, is what allows life to endure. When a cell divides, enzymes uncoil the DNA, unzip the strands, and copy each one base by base. The process is astonishingly accurate. Only about one mistake in every 100 million letters. But that single mistake is enough to fuel the story of evolution. The world changes because of the moments when the universe forgets its own precision. It's easy to imagine DNA as mechanical, but in truth, it is more like poetry written in the language of physics. The letters do not stand alone. They resonate. When two bases pair, their vibrations synchronize, like notes forming a chord. The molecule hums with frequencies too high for human ears, yet those vibrations shape its structure, influencing how it bends, how it folds, and how it interacts with the proteins that read it. In a sense, the code of life is not only a sequence but a song, one that must be sung correctly for the cell to survive. And so, within the double helix, we find a paradox that defines existence: stability through uncertainty, memory through motion, precision through chance. Life could not evolve without errors, yet it could not persist without fidelity. The double helix embodies both. It is the quiet compromise between eternity and change. As the snail carries its spiral shell through the grass, the same spiral unwinds invisibly within its cells. The patterns mirror each other, one carved in calcium, the other in carbon and hydrogen. Both are shaped by the same forces that guide galaxies and stars: attraction, repulsion, balance, and chance. The universe repeats itself in every scale. When you look at the curve of your fingerprint or the branching of veins in a leaf, you're seeing echoes of the same principle. Structure born from motion, order emerging from the play of randomness. DNA is not just a molecule, it is a reflection of the cosmos in miniature. It remembers and forgets in the same breath. And within that fragile memory, the smallest events, a proton tunneling, a base shifting, a vibration lingering slightly longer than it should, can spark the vast diversity of life we see around us. The double helix, in all its quiet perfection, carries the story of everything that was, everything that is, and everything that might be. As we follow this thread further, we'll watch how those tiny quantum decisions, those ghostly jumps of protons inside the helix, become the engine of mutation itself. It is here, in the smallest flicker of probability, that evolution begins. Inside the double helix, everything looks orderly. Two strands perfectly matched, turning in a smooth spiral like dancers in slow motion. But deep within that beauty lies movement too subtle for the eye, too quick for any microscope. Every second, inside every living cell, protons shift, bonds stretch and release, and the code of life flutters like candlelight. Most of the time, those motions cancel out, preserving the melody of the molecule. But once in a while, a note changes. A proton tunnels through a barrier it was never meant to cross, and in that instant, a mutation is born. It's easy to imagine mutations as dramatic events, as if lightning strikes the genome and transforms it in a flash. But the truth is quieter, smaller, and far stranger. A single proton, lighter than imagination, moves from one side of a molecular bridge to another. It doesn't climb or push. It simply appears there, a ghostly jump made possible by the laws of quantum mechanics. When it does, it changes the shape of the base pair, those chemical letters that write the story of life. The pairing still fits, almost perfectly, but not quite. It's a subtle misalignment, a whisper of difference. And when the DNA is copied, the cell accepts the new shape as truth. The change is microscopic, one letter out of billions, yet the consequences ripple outward. Over generations, these tiny shifts accumulate. Some fade into silence, others alter how a protein folds, how an enzyme reacts, how a pigment catches light. Most are neither good nor bad. They are simply possibilities tested by time. Evolution doesn't judge them. It lets them play. The environment decides which melodies will be heard and which will fade into quiet. The idea that quantum tunneling drives mutation might sound like something out of science fiction, but experiments suggest it may be real. Scientists have observed that hydrogen, the atom whose nucleus is a single proton, behaves differently when replaced with its heavier twin deuterium. The difference between them is tiny, just one extra neutron doubling the mass, but that small weight changes how easily the proton can tunnel. Deuterium moves less freely, less quickly. In one set of studies, bacteria were grown in two types of water: ordinary water made with hydrogen and heavy water made with deuterium. Everything else was the same nutrients, the same temperature, the same time. Yet something remarkable happened. The bacteria living in heavy water mutated more slowly. Their DNA changed less often. It was as if the song of evolution had been turned down by a single note. The difference couldn't be explained by chemistry alone. It pointed toward physics, toward the hidden world of tunneling protons shaping the fate of life. Think of it. The entire arc of evolution, from the first bacteria to the complex symphony of ecosystems we know today, might be traced back to the smallest of leaps, a proton's decision to take a shortcut through an invisible wall. That single act of probability could mean the difference between a creature that survives and one that fades into extinction. The grandeur of life may rest on quantum uncertainty, the universe's gentle refusal to be predictable. In the world of DNA, such moments happen constantly. The molecule trembles with energy. Its bonds vibrate, stretch, and shift in ways that blur the line between motion and stillness. At any moment, a proton may slip across a hydrogen bond, swapping one base's allegiance for another. Most of the time, it slips back before any copying occurs, a fleeting mistake corrected before it matters. But sometimes, timing aligns just right. The proton jumps, the replication fork arrives, and the change becomes permanent. The poet in us might call it fate. The physicist calls it probability. Both in their own way are right. When we think of evolution, we often picture it as a vast purposeful process. Creatures adapting, species competing, survival sculpting form. But beneath that grand narrative lies something much simpler and more intimate. Countless quantum coin flips. Every generation, in every organism, protons make choices that are not choices at all, guided by nothing but the wave-like nature of existence. Some of those leaps will vanish. A few will echo through time. It's humbling to realize how dependent life is on uncertainty. The same randomness that might seem to threaten order is what keeps the world from becoming static. Without tunneling, DNA would be perfectly stable, perfectly faithful, and perfectly lifeless. Change is the price of permanence. The same physics that allows particles to blur between states gives evolution its voice. You can imagine the genome as a vast library and quantum mechanics as a mischievous librarian. Most days she carefully preserves every page, but occasionally without warning she swaps a word, or even just a letter. Sometimes the sentence still makes sense, sometimes it becomes nonsense, and sometimes, by pure accident, it turns into poetry. The Earth itself has been shaped by these small acts of creative imperfection. A proton tunneling here, another there, over billions of years, the sum of those tiny motions has produced wings and scales, feathers and flowers, the blue of the robin's egg and the spiral of the snail's shell. Every colour, every scent, every pattern of life is the result of nature's ongoing experiment in uncertainty. Even the human eye, capable of perceiving a few photons at a time, was once nothing more than a patch of light-sensitive cells. Somewhere in the ancient past, a few mutations, perhaps triggered by the faint tunneling of protons, changed the proteins in those cells, making them more efficient at capturing light. Over millions of years, those changes compounded into vision. Now, through the very eyes shaped by that process, we can look back and see the light that started it all. There's something beautiful in that circularity. The universe evolving observers capable of recognizing its own subtle mechanisms. The same quantum laws that govern the birth of stars also govern the quiet mutiny of a single proton in DNA. Both are expressions of the same principle: motion without movement, change without force. And so, evolution becomes not merely biological, but cosmic. It's the universe exploring its own possibilities, one mutation at a time, guided by chance but shaped by necessity. In every living thing, from a blade of grass to a human being, those tiny leaps still happen, rewriting the code, pushing the story forward. If you listen closely, perhaps you can almost hear it. The faint click of protons tunneling, the slow turn of DNA copying, the whisper of uncertainty turning into form. Life, in all its diversity, is not an accident born from chaos, but a song played on the edge of possibility, a melody composed by the smallest motions in the universe. And as we drift further into this thought, the story widens once again. Because evolution isn't just the outcome of chance, it's also the dialogue between chance and necessity, between physics and purpose. To understand that balance, we must look at life itself as the meeting point between randomness and resilience, the art of stability built from uncertainty. The world around you is the result of uncountable coincidences. The colour of a bird's feather, the curve of a leaf, the rhythm of your own heartbeat. Each is the consequence of atoms choosing, long ago, one path instead of another. But that word choosing is not quite right. At the smallest scale, there is no choice, no intention, only probability. A proton doesn't decide to tunnel, just as a photon doesn't decide to travel. Yet from these blind uncertainties, life has built intention, structure, and beauty. It is the greatest paradox of existence, the random births, the meaningful. Think of it this way. Evolution is a conversation between chaos and order. Quantum mechanics provides the chaos, the unpredictable flicker that creates mutations, and natural selection provides the order, filtering what survives from what fades away. Together they make life a kind of balance beam, always swaying, never still, suspended between what might be and what is. It's tempting to imagine the universe as a grand machine, ticking predictably from one moment to the next. But when we peer closely enough, the gears dissolve into clouds of probability. What we call matter is a blur of possibilities, shifting faster than comprehension. At that level, nothing is certain until it happens. Not the position of a proton, not the alignment of a base pair, not even the spark of a new mutation. Reality, it seems, is not a fixed script, but a performance improvised as it goes. Yet somehow out of that improvisation, patterns emerge. Order rises from noise. Over billions of years, random quantum jumps have produced wings that ride the wind, fins that dance through the sea, and minds that can ponder their own origins. It's as if the universe, through its own uncertainty, has learned how to organize itself. The same equations that describe a proton tunneling inside DNA also describe electrons swirling in stars or waves of energy shaping galaxies. The scale changes, the story doesn't. When Darwin wrote about natural selection, he saw variation as chance and survival as necessity, two sides of a single coin. But he didn't know how small that coin really was. He didn't know that at the heart of every living thing, chance begins at the level of quantum motion. Today, we understand that every genetic variation, every new possibility for life, begins not with an external accident, but with the quiet physics of uncertainty. Evolution, in this light, becomes not just biological but physical, a continuation of the same dance that governs light, atoms, and space itself. If we follow this thread to its end, something profound appears. Life is not separate from the laws of the universe. It is those laws, expressed through matter in motion. The uncertainty that once made stars flicker now makes genes change. The probabilities that shaped atoms now shape thoughts. From randomness, awareness arises. You can see this truth in the smallest things. The colour of a flower that attracts a bee, the way a fish's scales shimmer underwater, the pattern of freckles on a child's skin. None of these were designed in advance. They're outcomes of mutation, filtered by time and environment. And yet, they feel deliberate, even inevitable. That feeling, the sense that the world fits together too perfectly to be random, might simply be a reflection of how deeply order is woven into chaos. Every living creature carries in its cells the memory of those quantum decisions. Your DNA, your most private signature, is the result of countless probabilities collapsing into reality. Each base pair that defines you exists because at some ancient moment, a proton took one path instead of another. In that sense, you're not merely a product of biology. You are the outcome of physics, a standing wave of probabilities that have settled briefly into form. And yet, you're still changing. Even now, as you read this, within your cells, DNA is being copied, repaired, and rewritten. Errors are made. Protons still tunnel. Mutations still bloom. Most of them will go unnoticed, but some, carried into the next generation, will alter the course of life yet again. Evolution is not something that happened long ago. It is happening now, quietly, in every heartbeat, in every cell that divides. There is comfort in that thought. It means that the universe is never finished. The story is still being written, one quantum whisper at a time. The randomness that frightens us, the unpredictability we often wish away, is the very thing that keeps life from freezing into perfection. Change is not a flaw, it is the heartbeat of existence. Some philosophers have called this the law of becoming. Everything from stars to cells to thoughts exists in a state of becoming, never fixed, never complete. Quantum mechanics, in its quiet way, makes that law possible. It allows the future to remain open, to be written and rewritten endlessly. It means that every living thing, no matter how stable it seems, carries within it a trace of possibility. When you look at the world through this lens, evolution becomes something more than adaptation. It becomes a dialogue between the universe and itself, matter asking what else it can become. From the first flicker of life in the ocean to the whisper of wind through the trees, everything is part of the same conversation. The randomness of a proton's leap and the perfection of a butterfly's wing are not opposites. They are steps in the same dance. Even the word mutation feels too narrow, too mechanical. Perhaps it's better to think of it as variation, the universe experimenting with its own design. Every species, every gene, every heartbeat is a variation on a theme first composed in starlight. The notes change, the melody grows, but the rhythm, that soft pulse of quantum uncertainty, never stops. It's astonishing to realize that you, sitting here in the quiet of your own thoughts, are part of that rhythm. The electrical signals in your brain, the light that enters your eyes, the breath that fills your lungs, all are quantum phenomena scaled up to the level of consciousness. In a sense, the universe is looking back at itself through you, wondering how chance became awareness. If you close your eyes for a moment and listen, you might almost hear it. The faint hum of probability beneath all things. It's the same hum that moves through a forest when sunlight touches leaves, the same one that guides a robin's flight, the same one that stirred the first cell to divide in a primordial sea. It's the sound of uncertainty turning into existence. And so, evolution continues, not as a march toward perfection, but as a perpetual unfolding. It is not progress in the human sense, but participation in the cosmic rhythm. Every living thing dances to it, from the smallest bacterium to the largest whale, from the whisper of DNA to the roar of galaxies. In that realization, something softens. The randomness that once seemed cold and meaningless begins to feel like freedom. The universe is not rigid but alive, breathing, changing, dreaming itself into new forms. From photons to robins to DNA, it is one story told in different languages, each translation adding another layer of meaning. And as we step quietly out of this exploration, the message lingers. Life is the physics of possibility made flesh. The same uncertainty that gives rise to stars also gives rise to you, and in that uncertainty you are infinite, a collection of chances still unfolding, still becoming. The world quiets as evening begins to fall. The wind slows, the air feels gentler. Somewhere a robin settles into its nest, folding its feathers for the night. In the soft blue hour between daylight and darkness, you can almost feel the invisible threads that connect everything, the same threads we've been following all along. Think of how our journey began. A robin's tiny compass tuned to the Earth's magnetic field, guided not by iron or instinct alone, but by quantum, entanglement. Two electrons born together in light, whispering to each other no matter the distance. Then there was the sense of smell, where molecules hum like instruments, and your nose listens not just to shape, but to vibration, to the quiet music of matter itself. We drifted next into the pond, where enzymes use tunneling to transform flesh and bone, where protons slip through barriers to make life move. From there, we followed light, the photon's journey from the sun to a leaf, finding its way through a maze of molecules with near-perfect grace. And finally, we descended into the spiral of DNA, where the smallest quantum leap, a proton tunneling between two bonds, became the seed of evolution. At first, each story seemed separate, a collection of unrelated miracles. But now, as you look back, they begin to blend together like colours at sunset. All these processes, navigation, smell, transformation, photosynthesis, mutation, share a single rhythm. Life, it turns out, is the art of turning uncertainty into order. Every living thing harnesses the unpredictable. Birds use entanglement to orient themselves in flight. Leaves use quantum coherence to capture sunlight without losing a single heartbeat of energy. Enzymes use tunneling to break and rebuild the bonds that keep you alive. DNA uses it to write the future. At every level, the improbable becomes routine. What physicists in laboratories spend fortunes to glimpse for mere fractions of a second, nature has been performing effortlessly for billions of years. Imagine, for a moment, a concert hall filled with instruments, each molecule, each atom, each cell playing its part. If one would play out of tune, the music would collapse into noise. But somehow, through the trembling of bonds and the flutter of electrons, life keeps the melody in harmony. It is a planet-wide symphony of particles learning to stay in tune. A robin's compass, the scent of rain, the sparkle of chlorophyll, the spiral of your DNA. They all hum to the same rhythm. Quantum physics, in its most intimate form, is not confined to laboratories or equations. It is the language life speaks when no one is listening. And perhaps, the more surprising truth is not that life uses quantum physics, but that quantum physics found a way to become life. It's a thought that humbles and uplifts at once. The same laws that govern starlight and black holes are at work in the breath you just took. The uncertainty that defines the quantum world, those flickering probabilities of where a particle might be, are the same uncertainties that make you unique. You're not separate from the physics that shapes the cosmos. You are one of its most intricate expressions. For centuries, science has sought to draw boundaries, to divide life from non-life, mind from matter, chance from design. But the deeper we look, the softer those boundaries become. Entanglement shows that separation is never complete. Tunneling shows that walls are not as solid as they seem. Coherence shows that chaos can sing in tune. Mutation shows that randomness can create meaning. The universe does not draw hard lines, it weaves. You might think of this web as a conversation between light and matter. Every photon that touches a leaf, every electron that moves through a cell, every proton that tunnels inside DNA is part of that dialogue. Across oceans, forests, and skies, the exchange continues, energy passing hand to hand, life to life, until even the smallest motion contributes to the whole. When you look at the Earth from space, a small blue sphere wrapped in a haze of light, what you're really seeing is this conversation made visible. The forests that breathe, the oceans that shimmer, the clouds that gather and dissolve, all are parts of one coherent system, driven by the same subtle principles we've traced through quantum mechanics. It's as if the entire planet is an instrument tuned by physics itself, and yet there is no conductor. No single hand guides this orchestra. It guides itself. That is the quiet genius of the universe, self-organization, born from randomness sculpted by time. From the vibration of molecules to the branching of trees, order arises because the laws of physics allow uncertainty, and life, in turn, learns to use it. If you listen closely to the world around you, to the rustle of leaves, the beating of your own heart, the rhythm of rain, you might sense that all of it is connected by a thread too fine to see, but too strong to break. It's the thread that stretches from a photon in the sun to the chlorophyll in a leaf, from the leaf to the breath you take, from your breath to the song of the robin at dawn. Somewhere, deep in a forest, a physicist might be calculating the energy levels of a molecule, while a bird just a few branches away is using that same quantum principle to find its way home. Nature, it seems, has been doing physics long before we gave it a name. There is a quiet poetry in that. The equations we write on paper are only shadows of the greater elegance already unfolding around us. Every living thing, by existing, participates in the experiment. We are not observers of nature's quantum world. We are its continuation. And perhaps that is the most beautiful realization of all, that life is not something added to the universe. It is what happens when the universe begins to recognize itself. When you think of it this way, the boundaries between science and wonder, between physics and poetry, begin to dissolve. You realize that curiosity, love, and even the instinct to understand are all extensions of that same thread, the universe learning its own song. As the last light fades and the robin's song quiets into the dusk, you can almost feel it. The vibration beneath everything, the gentle hum of a cosmos that has never stopped creating. It is not distant or abstract. It is here, in the breath you take, in the warmth that fills your chest, in the pulse that keeps time with the turning of the earth. And from that pulse, the story carries us toward its final thought, not about the physics of life, but the life within physics itself. Because perhaps at its deepest level, the universe is not a place, but a process, one that thinks, dreams, and listens through the living matter it has created. Dusk deepens. The forest breathes out a long, slow sigh as day gives way to night. The air grows cooler, scented with moss and soil. Above, the last of the sunlight fades to a muted gold, then to silver. If the morning was about the awakening of light, this is the hour of reflection, when all that brightness, all that motion, seems to fold inward and grow still. Yet in that stillness the story of life continues, softer now, but no less miraculous. Somewhere between the falling leaves and the stars beginning to appear, you can sense a quiet realization rising. Everything, from the robin's flight to your own heartbeat, has been part of the same unfolding. Life has not been an interruption of physics, but its deepening. What began as the trembling of particles has become awareness, curiosity, and thought. The universe, it seems, is not only alive, it is aware of being alive, through you. When you breathe, you exchange atoms that once belonged to stars. The oxygen entering your lungs was forged billions of years ago, in furnaces far beyond this world. The carbon in your cells was once dust adrift in a nebula. And the iron that colours your blood once glowed in the heart of a dying star before scattering across the galaxy. The universe has been building toward this moment for a very long time, the moment when it could look back at itself and wonder. Perhaps consciousness, the mysterious presence that allows you to listen, to think, to dream, is not something apart from the cosmos, but something it has grown naturally, like a branch from a tree. Maybe every act of awareness is the universe remembering what it is made of. You could say that thought itself is physics learning to feel. It's humbling to realize that the same laws that guide the spin of electrons and the fall of light also shape the flow of your emotions, the rhythm of your breath, the flicker of your imagination. When you close your eyes and picture the stars, those same stars are, in a way, thinking through you. They are not separate from your mind. They are the origin of it. In this way, consciousness becomes less of a mystery and more of a continuation. Just as photosynthesis allowed light to become matter, and evolution allowed matter to become life, consciousness allows life to become reflection. It is the next step in a long chain of transformations, the cosmos folding back upon itself, learning what it feels like to exist. Maybe this is why curiosity feels so natural, why every child, every scientist, every poet looks up at the sky and asks questions. Curiosity is not a human invention. It is the impulse of the universe itself, searching for its own meaning. Each question we ask is a photon returning home, a particle of thought tracing its way back to the source of light. Even sleep, the state you're drifting toward now, might be part of this cycle. The mind resting, resetting, dissolving into a deeper rhythm that echoes the expansion and contraction of the cosmos itself. During sleep, your consciousness quiets, but it does not vanish. It flows inward, joining the same hum that moves through everything. The vibrations of atoms, the slow rotation of Earth, the breathing of forests under the stars. In that silence, you and the universe are one continuous thought. If you listen closely now, you might feel it, the subtle pulse beneath all existence. It's in the whisper of wind through the branches, in the distant call of night birds, in the steady rhythm of your heartbeat. That pulse is the sound of entanglement carried across all scales, from the smallest quantum connection to the bond between minds, species, and stars. It is the universe speaking in the language of balance. Physicists sometimes say that everything is information, that the universe is, at its core, a vast network of interactions. But perhaps that information isn't just data. Perhaps it's experience. Each atom, each cell, each living thing contributes to the story of what it feels like to exist. The cosmos doesn't just evolve, it remembers. And that memory is written in you, in the sequence of your DNA, in the spark of awareness behind your thoughts, in the way you sense connection, even in solitude. Look up now, not with your eyes, but with your mind. Picture the night sky stretching endlessly above the forest. The same photons that began our story are still travelling, crossing billions of miles to reach other worlds. Some will never find a surface to touch. Others will fall into leaves, oceans or eyes, continuing the cycle. Light never truly dies. It only changes form. And perhaps the same is true of life, of consciousness, of everything that is. Maybe the universe does not think in words or images. Maybe it thinks in patterns, in waves and vibrations, in the exchange of energy that becomes thought, emotion, or dream. When you sit in quiet wonder, you are part of that pattern, part of the infinite conversation between existence and awareness. You are the way the cosmos has chosen to understand itself. Not all of it, but enough to feel awe. In the end, that may be the true meaning of life, not survival or progress, but participation. To live is to take part in the universe's unfolding story, to turn energy into experience, uncertainty into understanding, light into consciousness. You're not observing the universe, you are one of its ways of observing. Every heartbeat, every thought, every quiet breath adds another note to its eternal song. And so, as the night grows still, as the world settles into the soft rhythm of rest, take a moment to feel that connection. Breathe with the rhythm of this living physics, the entangled heartbeat of existence. You're not alone. You're part of the same fabric that holds the stars together. Part of the same wave that once left the sun and found its way into a leaf, a cell, a thought. The universe has been thinking through you all along, and now, as the day's light fades completely, let your own thoughts fade too. Let them scatter like photons into the calm darkness, merging with the quiet hum of everything. The story doesn't end here, it simply rests. Tomorrow light will rise again, and the universe will continue to dream itself awake. So, close your eyes, feel the weight of stillness around you. The forest is quiet, the stars are steady, and somewhere, deep within that silence, the cosmos is breathing. Through leaves, through oceans, through you. And so, we've reached the end of tonight's exploration. Whether your eyes are still open, or you're already floating somewhere between waking and dreaming, thank you for being part of this journey. If you'd like to wander with us again, you're always welcome to return. For now, let the world fall away. Time has no edges here, only calm, only light, only sleep.